Ciao Matte.
Ciao Ale, tutto ok? Ah, no,
A
no.
posto, grazie. Tu?
Mi stai seguendo da casa?
No, dall'ufficio.
Vuoi venire su J64? Ho provato per tutta la mattina.
Ok,
Vedi tu?
magari passo, sì.
Mm.
Adesso vedo un attimo.
Sì, sì, ma vai tranquillo, è per dire che comunque c'è l'opzione.
Yeah, thanks.
C'è anche Mark che mi ha salutato 3 minuti fa, non l'ho salutato. Dovrei preparare ancora magari una slide o due. Dico che se è presente il chi se ne frega arrivati a questo punto.
Sì, 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 vai, questa era... Matte, lo sai che stai registrando, vero? Già.
Sì, ma dopo poi magari si può tagliare, no?
Sì, si può tagliare, sì.
Sì, registro perché molte persone mi hanno detto no, ma non riesco a seguire solo una parte, o riesco a venire, oppure sono malato, o cose così, quindi...
Certo. Certo, certo, ci sta.
Renzo. Fammi vedere.
Ciao Matteo.
Hey Renzo, good morning.
Good morning. How are you doing?
Yeah, fine. No, I have a sleeping debt, but it's okay.
Good,
I'm
good.
preparing some slides tonight, and I'm like, eh.
You will get in rush. I mean, in kind of in the mood.
Yeah, yeah. No, it's okay. Let me see. Okay, let me try to share the screen. Can you see it?
Yes.
Cancel. Okay. Okay, so let's try to do a quick. Is it readable?
Yes, yes, it is.
Yeah. Yes, these slides are. This is quite small, right?
No, I mean it's fine. I mean I can read it. For me, it is okay.
Mm-hmm. So we do this test of see that everything flows.
Yeah, it is smooth.
Good. Now we do the dynamic. Like 200 slides plus the notebooks. I think I made too much material. And still I'm not happy.
Nice.
So at least this is the mental map of, I mean, how to navigate the tool. You're still seeing, right, the transitions, the
Yeah, everything.
hearing. Okay. We do a little bit of tree traversal. All clear. This was a quite transition. Okay, because this is the okay. 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 Everything clear?
Yeah.
Then of course we'll have to talk on it, but it's okay. Okay. Okay, so this you can see, right?
Yep, the tensor board.
Yes. The ternary features, histograms, also time series. For what? Ah, this looks like a new feature.
Morning.
Morning. Ciao, Miguel. And this one you can see, right?
Yes.
Hi, good morning.
Morning.
Ciao Matteo.
Ciao, Gianpaolo. Let's see. Morning, Nils. Sia. Marcello.
Morning.
Morning, Nils. It seems that 8:30 was too early. Sia. Okay, reach out to another channel. We will wait a few minutes to see if other people are joining. Yeah.
I guess Giuseppe should be joining from Trento.
Okay, thanks.
Yeah,
Yeah, we will wait.
I guess in a few minutes.
Perfect.
Matteo,
Mhm.
at some point I will need to quit.
Mhm.
So I'm sorry for that because yeah, I would have liked to follow your mini course entirely, but it's not possible.
No worries, because we will
So
register.
I guess you will start with an introductory
Yes,
the
overview.
first hour or first 2 hours more or less.
I mean, the introductory part should take like, I plan to do this like in 3 slots of about 1 hour 15 each.
Ah, great. Okay.
The first one will be introductory. The second one will start dealing with some small exercise and a demo of the tool. And the last one will deal with like the more advanced features.
Great.
But
Okay.
everything will be recorded, and yeah, I mean, so later it will be possible to
Yeah, to see it again. So
again,
good.
material. Yes.
Yeah, that's very good because we are planning, as I told you, to have a new PhD student here working also on this tool, using this tool. So yeah,
Yeah, that's
have a recording.
the intended purposes. Like even like people from Marco in Modena, like they attend. So
yeah, I guess so.
yes, but we can have also a call later, maybe if you want to discuss for details.
Okay, thanks.
Gianna, Moritz, Lorenzo, Florian. Okay. I don't know if it's worth to wait like 5 more minutes because there are many people that I know for sure are missing. I should be here. Okay, first note, next edition after 9. Okay. So just while we are waiting, I will start with a question. How many try to install the tool? Is there anyone that tried to, because I received some mails from Marcello in Bologna that tried to install and found the first error on my side. I mean, the installation, I think, went smoothly. There was like, I think which was not completely clear. Okay, so Ale and Moritz, perfect. Jan is installing it. Okay, so I mean, many people tried, so it's good. And it worked, so it's that's also good. Lorenzo is doing it, so yeah. I mean, I'm sorry because I know that I sent the mail quite late. Okay, also this work for him. Okay, perfect, good. We got late to the point because the publication process is mediated, and also I've been not super fast at completing the material, so perfectionism doesn't pay off. Also because anyway, as you will see, like some stuff, I mean, it's quite complex, and it's probably like to do everything in the way I would have liked to do it, like would have taken probably like 1 year, but okay. So maybe 2 more minutes and then we start.
Ciao Matte,
Ciao, Sia.
se mi avevi salutato non ti avevo sentito prima.
Sì, sento lontanissima. I hear you very far away.
Così meglio?
Yes.
Sì, anch'io dovrò andare via in mezzo, però tornerò dopo. Vedo che in I see that, sorry, it just came natural for me to speak Italian with Matteo. So the recording, like the workshop is recorded. Can we then get access afterwards?
Yes, we will share. We still have to decide. I have to talk with Frankon about the modalities of, let's say, sharing it and distribute the recording.
Mm-hmm.
But the intended follow-up is exactly like to publish it. So, I mean, or at least to make it available to people that request it. So,
Okay, so at least will be available if we request,
yes,
right?
yes, because
Okay, that's
one of the
perfect.
things the workshop is also like to have some recordings so that in the future when we will have to bootstrap projects for students or for us, like to work on the tool, like we would like people to I mean, we would like to give this to students first, and then once they've studied it, like they come back and
Yeah, that's perfect. That's great. Thanks.
welcome. Okay. 1 minute, and then I think we can start. Also because we are 30 people. And anyways, like I think 10 minutes of waiting is okay. Then people can actually also join later, even though I think they will. Like jumping on the train once it's running is like a little bit harder. Okay. Okay, I think we should start. Can you hear me clearly? I think so. Is anybody having any problem? Okay, good. So, good morning, everyone. Welcome to this edition of the Quant Lab virtual workshop. This is the first edition of the workshop. And today I will introduce you like to some basic concepts required to understand how to use this tool and how to benefit from it in your projects. So first, the idea of QuantLab. QuantLab is a tool that we developed, like it's a software tool developed to train, explore, and deploy quantized neural networks on different accelerators. The tool is based on PyTorch. PyTorch is a framework for deep learning, and to fully understand like its capabilities, today we will discuss several aspects. So the workshop will be organized in 3 parts, as far as I planned it. The first part will deal with computational graphs, which I don't know how many of you have heard of them, but they are the fundamental data structure underlying most contemporary deep learning frameworks. So I will give you an overview of all the basic ideas behind this data structure and its properties, and their application to deep learning, of course. Then, in the second part, I prepared some exercises because I would also like, at least I wanted to try to give you the opportunity to get your feet wet with the most tricky algorithms and processes behind the tool, which are those related to the graph manipulation. In particular, there are 2 kinds of graph manipulation. The first one is quite, let's say, lightweight, and it involves like graph traversal and leaf replacement. Whereas the second is more involved because let's say, it is based on more advanced algebraic concepts, like that have somewhat some kind of relationship with compilers, because in essence, they involve rewriting a graph, so looking for patterns in a graph and replacing sequences of nodes of certain types with other sequences of nodes of certain types. So the second and third part of the workshop will deal with, the second part will deal with like tree traversal and leaf replacement. And I will show you a demo of the tool of how you can configure experiments in QuantLab and use it to train networks. And in the last part, instead, we will deal with the more advanced graph rewriting functionality. Okay, so feel free to take notes and also like to make questions. Maybe I will like if I will be in the middle of discussion, I will just tell you, okay, maybe we can discuss like in a few slides. I will like have like milestones, like breakpoints during the presentation that we can use like to discuss. I plan to make 2 breaks. So the workshop will be split in 3 sections of approximately 1 hour 15 each, or at least this is the plan. Let's see if we can stick to it. If you prefer, like at a certain point, you have the feeling that I'm like rushing through the things because unfortunately I didn't have the time to try this the whole presentation out. Maybe you can just notify me so that we can like just go maybe more deep into some topics, and some of the others one I will leave them to the notebooks, which anyway are available in the repo, and that's it. So if the logistics is clear, we can start with this first part, which will be the more, let's say, didactical one. Okay, so outline of this presentation. This would be the more pedagogical moment of the workshop. Okay, this presentation will essentially deal with the things that I've just introduced you. So computational graphs and their application to deep learning. And in particular, we will also analyze a little bit the distinction between dynamic and static computational graphs and their impact on our tool. But even if this last part will become clearer towards the end of the workshop, then I will give an overview of the structure of QuantLab and of its subpackage QuantLib, which is the, let's say, the Python package containing all the functionalities related to quantization. And to do this, I will present you an overview of what is the full deep learning development stack, usually like from data analysis to model to program deployment. And of course, we will like go a little bit more in depth about the problem of QNNs. As a last thing, we will I will prepare a section, but this will become clearer during the exercises on the notebooks, because graph editing is, as I said, is the part where maybe we want to have a more hands-on experience in order to grasp the main concepts. Okay, so let's start talking about computational graphs and their application to deep learning frameworks. So first, we should agree on the terminology. Let's first review the terminology of graph theory. So because this is the basics of what we will be discussing next. First, every graph starts from a set, an non-empty set called the set of nodes. So nodes are entities, okay, living in the space, and but there have no mutual relationships as for yet. So to describe the relationships, like dependencies, we instantiate arcs. Arcs are arrows pointing from one node to another, and they can be directed. So in this sense, there is kind of a precedence relation, an ordering relationship between nodes. And this is, for example, useful to denote dependencies between operations or between priorities. And in some other cases, instead, the arcs can be undirected. And this happens when essentially there is no natural ordering of the connection. So there is no hierarchy, no priority between when considering two nodes. They are we just say that they are connected. And so this is called an undirected graph. Another thing that we will find very useful is talking about bipartite graphs. So bipartite graphs are graphs where the set of nodes can be colored in two ways. Okay, so each node can have one of two colors, and nodes of one color cannot be connected to nodes of the same color. Okay, so essentially this tells you, okay, nodes in the same partition, because like these, like since we have two colors, we have two partitions, like two subsets of the node set. And this creates a partition of the node set, and they will not have mutual connection. So as you see here, blue nodes, there is no arc or edge connecting blue nodes, and the same thing holds for orange nodes. So, okay, before we see like the application of these like graphs to neural networks, I cannot assume that all of you know about neural networks and supervised learning. So I will try to give you a quick overview of what this supervised learning framework does. So the basic task of supervised learning is trying to find out a good approximation of a function that we don't know. So for example, imagine that this set X is the set of images, okay, of RGB images that contain 200 by 200 pixels, and Y is a finite collection of classes, also of semantic labels that you have to attach to an image to say, oh, okay, this is a house, this is a plane, this is a cat, and so on. The point is that usually we don't have a good algorithm like to instantiate this function, so we need to find an approximation starting from data. The first point is that before we do any attempt at approximation, we need to be able to evaluate the quality of our approximation. So the first question in machine learning and supervised learning is, how can we tell how good is an approximation f of the function f star? And to do this, essentially, we use a very intuitive concept, which is that of loss function. A loss function essentially compares the outputs of two models, as you can see like here in the lower equation. So Y is a label that we know from the data at our, let's say, that we have available, and f of X is the prediction of our system, okay? And this L function compares them and returns a measure of the loss or the error like made. So this loss function, it will be 0 if the label, the real label provided by the data is equal to the one predicted by the model. Okay, and it will be instead far from 0 if these two labels are different. So what these like, okay, I know that for some people, like whenever we see like all these integrals and symbols is not very clear, but the point is that we need to assess how distant is like a prediction from the label. And this just tells you, okay, just look at all the images like in your data set. So in order to assess how good a function is, we better not assess it just on a single data point, but we should take the expectation over all the possible input-output pairs that we have available, or ideally all the possible existing input-output pairs. So this like is called a functional because it takes an input like this function f. We assume that the distribution over the data xy is given, and it will return like these average accuracy, average, let's say, quality of the approximation. Okay, again, another slide packed of mathematical notation. So when we go towards like, when we want to learn this model with a machine learning system, the common way is to use functions which have part of the data, this denoted by this parameter theta, which can be learned, okay? So this like blue f of theta and x is, let's say, a program where some of the data is learned during the process. Then we use like, we can use data. So what it means like this is like, this like second item means is that we will never be able to know the real distribution of the data because we will never like be able to sample all the possible images in the world. Even like we wouldn't know like how to store them because like if the images contain 200 by 200 pixels, it's already 40,000 pixels, and each of them like has 3 channels, so it's 120,000 bytes for each image, and each byte can be in 256, which is 2 to the 8 possible configurations. So you see that like we'll never know like all the real mu, the real distribution of all the images. So what we do is we approximate it with the distribution coming from the data. This notation is quite convoluted. I took it from my thesis. It's okay. It's quite annoying, but what it means is that each data point, so the same image can happen maybe more frequently, because some images can happen more frequently, and but in a set usually you don't have duplicate elements. So this is just to tell you each pair input output appears these many times. Okay, so what we do is approximating the real measure of the data with like the so-called empirical distribution. And this, if you plugged it inside this integral, okay, you just get like this kind of expression here on the left side. And the point is, how do we learn these parameters theta, this part of the data of your program? And if the function f is differentiable, we can take the gradient of this like loss function, okay, with respect to the parameters. And then we take a step denoted by this minus eta against the gradient to optimize the parameter and try to reduce the value of the loss function. Okay, I hope everything was clear. So let's see how this like relates to computational graphs. So computational graphs are specific graphs which are, as we said before, directed and biparted. Okay, why biparted? Because in essence, when you have programs, you have pools of memory where you read from or write to, so the operands of your operations, and kernel nodes. So like nodes representing the real pieces of code, okay, that fetch data from memory nodes, execute operations, and write the results to other memory nodes. And so the arcs going from like from memory nodes to kernel nodes, they represent the read operations, okay? Whereas the arcs going from kernel nodes to memory nodes are write operations. One crucial property of these graphs is that each memory node is the result of at most one operation. So no, I mean, it is usually if you have like the situations where 2 operations write to the same array, you can actually rewrite it, rewrite the graph in a way that each operation is writing to just one array. Okay, an example to understand better. Imagine that you have to compute this function, okay? So W2, B1, W1 are parameters, okay? X0 is some data in input, and sigma, this like is sigma, is like an activation function, a so-called activation function, which is like a function that distorts, is not linear. So it does not like, it's not like of the form y equal k by x. So this is like something that distorts your information. So if we want to write this as a computational graph, we start by the first operation. So we take as inputs x0 and w1, which as you see here, they live in memory nodes, which are the square nodes. These nodes are fetched from the blue node, which is the matrix, the scalar-scalar multiplication, okay? And the result is written to this this other memory node. Then we want to add a bias, okay? So what we do is we do an add operation, we fetch the result of the previous operation, we fetch this B1, and we sum them up and write the result in this new memory node. Then we want to apply this nonlinear distortion to this number, so we apply this function. You see that the result of the previous operations is fetched by this blue node, and the result is written in another memory node. And in the end, we multiply the result by another number W2. So this is like a computational graph, okay? Then we said that we can optimize neural networks, okay, by performing gradient descent. So gradient descent requires to compute gradients by definition. There are mostly three ways of performing differentiation, okay? The first one is symbolic differentiation, which is, let's say, a general case, including the process that we learned at high school of taking derivatives, okay? So essentially, you use like the rules of differential calculus to, given a function, compute the gradient. From a computational point of view, this means that you want to have a system that, given a function, which is depends on some parameters and maybe on some inputs, you can compute this gradient as another program. So you manually or like automatically compute a program that is equivalent to computing like this gradient of this function L, okay? So the drawbacks of this approach to differentiation is that doing it automatically might be impossible if your functions are very complicated, okay? And if you want to compute it by hand, which you can always anyway do, or in most cases you can do, is for sure time consuming, and I don't know for you, but for sure for me is error prone. The other way of performing differentiation is numerical differentiation. So usually this is like the approximation approach, but is like this is really like at the basic building block even of the formal definition of derivative. So you take the function, okay, based on the definition, you evaluate a different, like you try to modify the value of the variable with respect to which you want to compute the derivative. So in this case, you take the parameter, you add something, and you say, okay, how much did this function change when I added this like variation? Okay, so I evaluate the function in two places. I take the difference, and since the derivative, or anyway, the directional derivative is like this divided by the amount of, let's say, change in the input, I just compute this divided by h, by the norm of h, if I'm talking of vectors. The problem of this approach is that it is like an approximation, and you are computing it only with respect to the direction defined by h, which is your change. So when your theta, like your parameters or your input, are multidimensional, you are very likely to make mistakes. So the solution to this is automatic differentiation, okay? Automatic differentiation is another approach which is based on the chain rule. So it's applicable in cases where the functions that you are differentiating is a composition of functions, okay? And the critical requirement of this approach is that each operation in your sequence, you can compute gradients of the output of this operation with respect to the inputs. There are two ways to perform this. You can compute the local gradients. These are called the local gradients while you proceed forward in the graph, in the computational graph, or you can compute the gradients when, like, after you have finished like computing the outputs, you go back and compute the gradients. This is called reverse mode automatic differentiation, and it is what we call, like in deep learning, backpropagation. Okay. Usually the advantage of using backpropagation with respect to direct mode automatic differentiation is that you do less computations. I'm sorry that I was not able to like put down the slide that I had like written on paper, but I mean, for who's interested, I can like give more details maybe later. Okay, so differentiable computational graphs. As you see here, I essentially try to just report the operation that I showed you before. Okay, so the same graph. If you notice, like I have like reversed the direction of arcs. Okay, so now instead of going like from left to right or from top to bottom, we go from right to left or from bottom to top. And essentially what ultimately like the results of this operation are computing like gradients directed towards the parameters. Okay, so you see that here we compute like the gradient of this L, which is the loss function with respect to the parameters. Okay, So this is the basics of computational graphs and why they are important to deep learning, okay, and especially differentiable computational graphs. Now I'm going to show you how these computational graphs are used by different deep learning frameworks. And in order to do this, we will do two things. First, we will look at static versus dynamic computational graphs. And later, I will show you how different frameworks abstract on top of these existing graphs. So let's consider this graph, okay? This is I just took the graphs of the previous slides and I flipped it, rotated it 90 degrees clockwise, okay? And then I added some small operations on top. So static computational graphs. The graph is defined before executing any operation, okay? So you essentially create placeholders, you create empty arrays. The data contained in the arrays has no meaning, okay? You just allocate memory. If you think to a program, you're just allocating memories and defining permissions for which operations can write to which memory region, okay? The pro of this approach, with respect to, as opposed to dynamic computational graphs, is that you know the structure. You are forced to think to the structure of the graph beforehand, okay? The cons is that since you have to think about this and plan for it and implement the program, might be time consuming and lead to you spending more time onto thinking of what you have to do. But the advantage is that it will make it easier to manipulate the graph and, for example, transforming the graph. And in fact, as we will see later during the workshop, this is one of the introduce some complications in QuantLab that we have to take account for. So let's say that we want to build the computational graph. So we start by defining placeholders for the inputs and the labels in the case of a neural network, okay? Then we define this operation, which is the multiplication by a matrix. Then we add another operation, which is the addition with a bias, okay, so a translation. We add some nonlinear distortion, so an activation function, another linear operation, so multiplication by a matrix. And finally, we apply the loss function comparing the prediction here on the right to the label here on the left, and it returns the value of the loss. Now we initialize the parameters, okay? So what you want to do when training a neural network in a framework using static computational graphs, you initialize the parameters, okay? And now you feed the input to the placeholder. So in these memory arrays, in these memory pools, you write some data coming from the external world. This depends on the data set that you have at your disposal. Then you start and you push the information through the graph. So you call the first operation, which fetches the input and the weight and writes what is called a feature map. These intermediate arrays are called feature maps, to distinguish them from parameters, which are the nodes on the right, okay, and from inputs, which are these, which is x, and this, which is y, so input and output of provided by the data set. Now we do the addition by a bias, then we compute the nonlinear activation, again a linear transformation by multiplying by a matrix, and finally we compute the loss, okay. So now we reverse the edges, okay? Now this was the forward pass. Now we do the backward pass to compute the gradients, okay? So we start by computing how much the loss was off with respect to 0. And so we want to update, we want to know how these two nodes should have changed their content in order to reduce the error. Of course, the data, so because y is data, y is the label provided by the data, so this cannot be changed, so no gradient can flow here. We compute just the gradient with respect to the prediction of the network. Given this, we again use the local differential. Remember that each node must be differentiable in a computational graph, that if you want to use it for deep learning. And these computes on the right, a gradient going towards the parameter, and above a gradient, how this feature map should have changed in order to optimize the value of these the prediction of the network. And again, we go back. So you see that we are pushing back the gradients, okay, until we have access to all the the derivative of the parameters with respect to the loss with respect to the parameters. Now that we have computed the gradient, we can actually update the parameters, because remember, gradient computation is different from gradient descent. So we have the gradient and we can apply a gradient descent algorithm to update the parameters. Okay, so this is done. Dynamic computational graphs, okay, instead, they essentially, you just put in place operations and you implicitly define which operation should be called first, but we don't instantiate, we don't allocate memory for the feature maps or the input and outputs. This is done usually after initializing the parameters, okay? So we initialize again the parameters, and then depending on the structure of your script, of your program, we will just like create the memory arrays for the inputs and labels. And we start calling the operations, which like the order of the calls is determined by your script. And you see that the graph is like triggered and built dynamically at runtime, okay? And this structure at a certain point during your forward pass exists. So this link again is rebuilt. Like the difference is that we didn't have like, we don't have a static structure as for static computational graphs. So again, we reverse the arcs, okay? We compute how the loss should diminish, the direction. We want to compute the direction in which the parameter should change in order for the loss to diminish. And again, we go. But as you see, once the gradient is available, this structure is forgotten, okay? The link, this structure is free for the garbage collector to be removed. So what we preserve is just like the information about how the parameters should change. We update the parameters and the garbage collector just cleans up your device's memory. All clear? Okay. So, okay, to conclude this section, I will show you how like different existing frameworks or standards interpret computational graphs, because this will make it easier for you to grasp like also the working of QuantLab. So the first thing is essentially, let's start by what we can think of as the assembly of computational graphs, which is the ONNX. ONNX stands for Open Neural Network Exchange Format, which has been developed by many companies, especially I think Microsoft and NVIDIA. Also Google and Facebook anywhere in the consortium, so they are like pushing for defining the standard. And in this standard, you have some, let's say, standard operations like convolutions, like in the sense of matrix multiplications, or other, so really convolutions which are specific matrix multiplications, bias additions like nonlinearities and so on. And in this kind of format, you actually see a computational graph as a bipartite directed graph. In TensorFlow, I mean, now in the last years I've been using PyTorch, so here I will tell you how TensorFlow worked, at least the last time I've used it, like which is 3-4 years ago. So don't really like take this as it is right now, because I'm not really sure, but I think it is still quite similar, and this at least was the idea at the time. So in this case, like when you wrote a network in TensorFlow, a TensorFlow supernode, okay, when you define a TensorFlow graph, TensorFlow uses static graph, okay, and you define super operations, super nodes, okay, which are like denoted by these blue underlying patches, which group together kernel nodes and some data memory nodes, which can be parameters, the one on the right, they can be feature maps, like the orange one or this one, but in some cases they group together also groups of multiple like basic nodes, okay? So you don't see from the outside that there is actually this feature map at a certain point, okay? And so from the outside, like you can identify like each edge connecting nodes like between different cells with the last memory node of the cell, okay? So this led to the interpretation of nodes represent operations and edges represent data flowing between operations. Because this graph can be also visualized like this, okay, where you have these big nodes which actually contain kernel and also some data nodes, and you have some data being communicated from the one to the other, so being fetched from one node from the previous one. Instead, in PyTorch, like this is like PyTorch works now, so these I'm more like, let's say, confident about. What you have is that once you create the network, you just put in place these structures, okay, where the operation nodes, remember, since the graph is built dynamically, these operations are not yet created. These will be I mean, they live in the memory of the Python interpreter somewhere. They are fetchable, but they have not been instantiated yet. So what the only thing that exists when you create with the constructor method of a PyTorch script, a module, what you actually are creating for the moment is just the parameters. And of course, like the pointers to the correct operations, but you have not then called them or like fully registered them to do the full graph construction and backpropagation. Okay, instead, so in this case, what we will see, like when you build the PyTorch network, is just a bunch of super nodes, which actually contain some parameters and hyperparameters or constants, but they have no mutual connections yet. Okay, this happens when you call the forward method. So when at runtime you actually get data flowing through your network, and this structure will be created, okay, in the same stack like way that I showed you before. Okay. So as a last example, like this is like more of for niche, but for people working on neural architecture search. So neural architecture search is a fancy name for model selection. So the problem of selecting the best way to arrange functions and build up a successful model, a model which is capable of predicting very well the label for your data. This structure, this is a cell of this Nash bench 201 space. The Nash bench 201 space is a space of topology of different neural network architectures, okay? And it is based on, I mean, each network in this space is composed by stacking multiple cells built like in this way. The problem is that you don't see all these like memory nodes and operation nodes, but the tool somehow masks them. I mean, the dataset somehow like represent this as edges connecting just like critical arrays, like critical memory nodes, which are like the 0, 1, 2, and 3. So you see that from 0 can go to 1. 2 receives data from both 0 and 1, and 3 receives data from all the 3 previous like memory arrays. And on data, these are labeled with the name of the operations that are actually joining the 2 memory nodes. So as you see, starting from a very common and basic bipartite graph representation, each framework and each problem like builds abstractions in a different way on top of them. Okay, so if you have any question about this first part, I'd be glad to take them.
Matteo, I have a question.
Yes.
Can I ask? Well, I'm a bit confused about the definition of bipartite graphs. So in particular, I didn't understand if the 2 classes of nodes are essentially the parameter class, so the class of nodes representing parameters, and all the rest. And the rest is also, say, data nodes and also operand nodes.
Okay, so exactly.
So am I correct or not? Because
well, the fact is that memory nodes can represent both parameters. So in this case, so these nodes, okay, the yellow nodes here are memory nodes. So they are part of the, let's say, the orange partition, okay, but they represent parameters. So data of your program that can be changed during the learning algorithm, but essentially characterize your program. Instead, you have these, all the remaining orange nodes, but for this one, let's say the node on the left here, the one on the bottom, the one on the corner right, bottom, and one on the top, all these three memory nodes, they are feature maps, but they're still nodes of the memory partition because they are still operands. The top one and the left one are, they're not feature maps because they actually depend on your data set. So you will have to transform files in your data set to get data into these two nodes. And these will be arrays, but they're still memory nodes. So they still belong to the memory partition. But these cannot be modified by anyone because this essentially is how the external reality looks like. Okay. And the loss and the prediction instead are, let's say, we can consider them features because they actually depend on the processing of some function, but their semantic is slightly different from that of features because they are actually what will be, the loss itself is used to determine like the learning signal, whereas the prediction will be fed to the next program in your pipeline because usually you use neural networks as small functions in the context of bigger systems of programs. I don't know if this answered you satisfyingly.
Well, more or less, because I was just looking at the arrows, and according to the definition you gave at the beginning of bipartite graphs, so it seems that the arrows are creating two classes, and one of the two classes contains both, say, disks, blue disks, and some part of the squares, right? Because they are all connected. So while the squares on the right, the three ones, for instance, that you have in the column on the right, rightmost column, they are not say not connected each other, so they belong to
no, because the point is that they
should belong to.
No, but the point is that you see that there is no arrow connecting orange to orange, right? And there is no arrow connecting blue to blue. In any case, in any of these cases, right? Can you hear me? Gianpaolo? Guys, can you hear me?
Yes, can still hear you, but not Gianpaolo.
I have some connection problems, sorry.
Okay.
That's
okay.
my problem.
Point, I think I see. The point is that to be bipartite, there must be no arc connecting nodes of the same color. So there is no, here in this graph, there is no arc connecting orange to orange or blue to blue.
Okay, so you mean single arcs, not paths?
No,
so
single arcs. Single arcs.
Okay, thank you.
Okay, good. Okay. Anybody else has any question? Okay, I've already killed you like after the first section of the workshop.
Can I ask something? Sorry.
Sure.
I wasn't. I mean, I really didn't understand what was the main reason that you mentioned ONNX there. I mean, I couldn't connect it with the next part. Can you please repeat that part again? Sorry for that.
My point is that the different deep learning tools or deep learning, let's say, in different deep learning contexts, you use different tools, right? You can use PyTorch, you can use TensorFlow. People working in NAS have access to this NAS bench 201. And the point of ONNX is that this was developed as a format to exchange parameters and descriptions of networks between different frameworks, like for example, between TensorFlow or PyTorch. So in order to allow this kind of translation, you need access to something to which each model can essentially be translated. Okay, to use it like as a lingua franca. Okay, and the point of ONNX is that in ONNX graphs, if you like go inspecting an ONNX description, you will find list of descriptions of operations, and each operations will fetch data from memory pools, like abstract memory pools that have like a shape. So these are arrays which like several dimensions, and dimensions which are all integers, like integer size. So the point of ONNX is that this is like a format that is used to which each network written in the most important deep learning frameworks can be written to. I don't know if this is sufficiently clear, because I know that like there is some details that might be missing, and maybe I didn't like express it like in the best way.
Thanks for the clarify. Thank you.
Is it clear now?
Yes, I think so. You mean that with ONNX, we are actually able to kind of translate these different types of structures that we have in TensorFlow and PyTorch for defining the graph. So we can, yeah, we can.
It is not straightforward, but you can do it.
Thanks, I get it.
Perfect. Any other question? If not, I think we can proceed by explaining the structure of QuantLab. Okay. So in the second part of the presentation, we start like looking into QuantLab and its structure. So this will be more of an overview. Okay. Later, I will also give a demo to show you like how to use the tools. But in order to understand what is happening, I think it's best that I tell you like what is the structure of the project. So to understand the structure of the project, we first, we started by looking at how the development of a deep learning application flows. So usually at the top level, okay, from an abstract point of view, we start from the data analysis. So you have some files that you might have collected. I mean, they might be public benchmark data sets such as ImageNet or Coco, but you might also have private, like proprietary data from some like company manufacturing equipment, a piece of equipment, okay? And you want to, you cannot figure out an algorithm to map inputs to outputs. So you start by analyzing your data, and at a certain point, you might realize, oh, maybe we can use a machine learning model. And since deep learning works so well, and maybe your data is, I don't know, images, and convolutional neural networks work very well, we choose to design a neural network, okay, a deep neural network to process the data and to map inputs to outputs. And then, of course, we want to train the model. So we feed data into the design DNN. We choose a gradient descent algorithm, and we train the network for as many batches, as many epochs as we want. Essentially, the training algorithm for deep neural network is an iterative application of gradient computation and gradient descent. So you have the backpropagation plus a step of what is called stochastic gradient descent, which is this is not the topic of the workshop to explain exactly why exactly this is stochastic. The whole point is that this is an iterative training algorithm. So it involves multiple steps, and at each step, the same thing happens. You feed data into the network, you compute the predictions, you compare predictions with the labels, you compute the gradients via the backpropagation algorithm, and then you use gradient descent or some variant. So when you hear like words like ADAM, SGD, ADAGRAD, RMS prop, these are variants of the SGD. They don't involve backpropagation. Backpropagation is a computational method to compute gradients, as we saw. Then once the network is trained, for some people, like especially working at a high level, their work is done because the model is there. Maybe all the statistical accuracy and validation metrics have worked like out well, so that's good. But the work is not finished for if we want to deploy the trained model on some server, or maybe if we want to deploy it on some embedded platform for which we have to generate code. or compile using specific instructions, because there we also have to perform these steps, okay, which are platform specific. So they depend on the end device on which we will deploy the network. These include graph optimizations, such as tiling, node fusion, of course, code generation. So you can generate like real source C and C++ code, which is still like platform independent, but maybe it contains some optimizations that like you've wrote some specific C and C++ template that are optimized for your platform. And then you pass this source code to your machine's compiler that generates code. And then you're able finally to load the program into the device's memory, and the OS will take care of executing it. So before we delve into quantization, let's look at how QuantLab can manage general deep learning experiments. If you downloaded QuantLab and like looked into the folder, you will have noticed that it has like these three files, two folders, one named systems and one named manager, and a file named main.py, which is like the interface to access all the services provided by the tool. So let's start by investigating what the systems package is before we delve into the flow. Okay, the system package essentially is a hierarchy of namespaces. Okay, so inside it you will find like 3 levels of hierarchy. Okay, defining like what in our view you can think of as the general model of instantiating machine learning systems. Okay, so you start by something which is like a library of general components. So in any machine learning system, you have something which you can recycle independently of the data set, independently of the network topology that you're trying to solve. This, for example, is the case for some loss functions, some gradient descent algorithms, and essentially the utils sub-package, you can think of it as an extension, as a QuantLab specific extension of some of the tools exposed by PyTorch. Okay, so for example, this can contain custom learning rate scheduler, custom optimization algorithms, custom loss functions that you can apply to many data sets and many networks independently of the data sets and of the network itself. Then when you want to create, the point is that the things start getting specific when you want to apply your deep learning system to a specific data set, okay? And the data set we refer to as a problem, okay? In QuantLab jargon, we say that the data set is a problem. And to create this blue folder, you have to use like this script, this bash script, and pass the name of the folder, the programming package that you're going to create, because this this script will create this blue folder, which and will create like an init.py file inside it, which turns this folder into a Python package, and it will create like these utils and a link to the real data folder. Because these like utils is like utilities that are specific to this data set, okay, to this problem. So for example, some specific function that takes files in this folder and transforms them in a way which in general like do not depend on the network topology. So let's say, for example, these are images and you want to adjust their brightness. It doesn't matter which network topology you will apply to the data. Change in the brightness is something that does not depend on the network that you're going to apply on top of the data. So you have the possibility of defining this here in these utils. You cannot define it here because you cannot apply brightness enhancement to data set including acoustic events, for example, okay? Because time series related to sound have no relationship to I mean, they have no notion of brightness in the sense that you think of it for images, okay? So, and these blue packages, we call them problem sub packages, okay? So they are the, let's say the top, the second like highest level of the hierarchy. Then if we can of course repeat this for adding other problem packages, okay? But then if we, given a data set, we want to instantiate a specific network for it, okay? We can use, we have different choices for the program that we want to throw in the data and try to learn the function. And so what we do is create using this, okay, this, I should have checked the slide twice, 3 times, because here, like you have configured / it should be topology.sh, okay? And you see that I give it the name cipher10 and a name of the network topology, in the case VGG, okay, which stands for Visual Geometry Group. It is a popular convolutional neural network architecture. Now it's quite outdated, but still like a good benchmark, at least for like prototyping your ideas. And you see that when you create these like namespace here, it will create several things below. So a logs folder, which will like store where QuantLab will store the results of your experiments, preprocess that contains all the Python abstractions used to, that are instead specific to the data. So here you can contain some topology agnostic, but dataset specific transformation. Here you have transformation that are both data specific and topology specific. Then you have the topology itself, so the PyTorch model itself, the post process. So let's say to connect the output of the network to transform it in a way that it is compatible with like the generic, the topology agnostic format of the outputs. And then you have a configuration file, because we will see later in the demo, you can govern QuantLab experiments by using config.json, which are like configuration files, okay? And of course, you can, as for the problem subpackages, you can do the same process for topology subpackages. So you can extend, you can add as many as you want inside the namespace of the data set. Okay, now the manager package instead contains all the utilities that QuantLab uses to handle your experiments. And it mainly contains 5 sub-packages. The platform subpackage contains the abstraction which is needed to handle the hardware and OS related aspects of running experiments. So for example, it controls like GPU, it decides like how to condition the creation of PyTorch objects based on the number of GPUs you have access to. It can coordinates, let's say, communications between different processes in multi-process runs, because like QuantLab also supports distributed computing with Horovod, which is a plugin for PyTorch, an add-on, okay, something like an abstraction that a software that you can install on top of PyTorch to run experiments on multiple processes and therefore also on multiple machines. This is useful if you want to scale to, for example, supercomputers, okay? But this is like everything that is not strictly related to the scientific, statistical part of machine learning. Then in the package flows, we define the services. The services are the commands that you can access through the facade file main.py. Okay, so here you find the implementation of this. In the logbook, instead, this is an abstraction that we use to mediate, okay, all the interactions that a QuantLab session has with the storage. Okay, so for example, storing the checkpoints, storing the statistics that you can inspect later about an experiment that is running, okay? And everything is mediated by the logbook. Assistants, instead, are factory-like, builder-like objects that QuantLab uses in the flows to build up the components needed by your experiment. So data loaders, the neural network itself, the components of the training algorithm, so gradient descent plus the loss function. And finally, the meter. The meter is like an extension that we developed to make it easier to use to track statistics. So this is like something that we thought a little bit about to make it easier for users to register statistics that are not so easy to track in PyTorch, okay? Okay, then being aware of this structure, let's see how, for example, we can interact with the 2 most important QuantLab flows. And flows are, remember, the services that QuantLab exposes to the user, okay? So first we start by configuring an experiment. So before you can train a network, okay, you need to, and supposing that all this material is ready, then later I will also show you how to prepare this stuff. We have to configure an experiment. So we have to tell QuantLab how to get ready for running an experiment. We do this by issuing this command, python main.py, and we have two flags telling the problem and the topology, so how to navigate the system's namespace and configure. So the entry point is the facade file, main.py, okay? And when you create this, like I use this gray box to denote the fact that a Python interpreter has created its space, its execution space, okay? And here, entities will appear that will describe Python objects living in the interpreter's space, okay? So the first thing is that Python main.py, you have to look first at this like flow here. So the flow is a keyword that you pass to the facade, okay? And it will direct the execution to one of the flows described in the flows package. You see that here below I will be highlighting the components that like of the where the things like the entities is defined, the entities are defined. The flow, when started, you will notice that, okay, I have to create a logbook. And so it will go into the logbook, it will look at the definition, it will create an object of type logbook, okay? And then, using these two flags, the logbook will navigate the system's namespaces down to having access to all the entities defined below the cipher10 folder in this package. And of course, like also the utils packages will be accessible. But for the moment, we are navigating like here. So you see that here there is this config.json, and this config.json is like, let's say, a public version of the configuration of your experiment, which you have to edit by hand. And after editing, this will be, and after editing it and issuing this command, it will be imported into a config dictionary. This is a Python data structure. Once there, like the logbook can forget about the public config file, it will apply some modifications. So for example, you can create seeds that it can reuse when you are resuming an experiment that maybe can crash, okay? So I will seed it in order for enhanced replicability or doing other kind of actions of this kind. And then it will write it in the logs folder. So as you see, if you see here, this has become highlighted. And essentially, I will store this private configuration in another JSON file, but in a private folder dedicated to this experiment. And then the flow finishes, the structures are destroyed, and we are ready to go on with the training. Okay, so the next flow that I will tell you about is about training DNNs. So training DNNs in QuantLab, again, we access the services provided by main.py in the facade, okay? So we see that this time the flow triggered by the command is train, okay? In this case, since it's training, I will also look at the platform because I want to optimize stuff. So QuantLab like goes into the platform package and creates an object to handle like all these, let's say, complicated transactions, okay? So we again create the logbook. And again, we traverse the system's namespace in order to fetch all the symbols defined in these folders, like below this cipher10 folder, okay? And this time, you see that we pass the flag telling, hey, this is like, you should read the config from experiment 0. Okay, we are running experiment with ID 0. And if you notice, it won't read it from like here, the public file, but it will read the file that we have prepared during configuration, okay? Because this will have specific details of the experiment that we want to run. Okay, at this moment, okay, we are ready to start creating the entities that are needed to run the experiment. And for this reason, we use the assistants. Okay, this is why assistants exist. And with assistants, we start with the data assistant. The data assistant will use the entities defined in the utils sub-packages, both at the top level namespace and at the second level namespace, so the data set specific. It will also, since data needs to be prepared in PyTorch in a way that it is compatible with what the network will take, we also need to know how to pipe the data to the network. So to create the data sets, the so-called data loaders, which are like wrapper for dataset structures in PyTorch, we need to know also topology-specific information. So we need also to have access to something that is defined as pre-process package. And of course, we need to have access to the data of this data set, of this problem, of our problem. Using a similar logic, another assistant, the network assistant, will look at the definitions available like in this vgg.py script, so in the topology script, plus the utils packages. And it will prepare to create, it will get handles on these objects, get ready to create them on demand. The same thing will happen for the training. And since training has to deal also with, has to compare the output of the network with the labels, we will also look into this post-process package, okay? So again, as you see, the utils is always accessible, but the real topology specific information is hidden in this post-process package. And then we have the meter. And the meter is like, again, our abstraction to facilitate access to logging services offered by PyTorch, which is not super intuitive, at least in the beginning. And as you see here, some of these facilities are defined in the meter package, which is general purpose for exactly the reason why, because like this is intended to work on as many PyTorch networks as possible. Then of course you can always define something network specific in the postprocess.py or dataset specific in the utils.py. And this is a package. Okay. Okay, so everything is ready. So in the training flow, we have built up the assistants, and the assistants know how to build the objects configured by the config dictionary. Now training starts. So we create the entities. So we create the training loader, the the validation loader, the network, the loss function, the gradient descent, which is composed by the optimizer and the learning rate, and possibly the learning rate scheduler, and the meters. And okay, they start interacting with the logic that depends on the working of PyTorch and in general of neural network training, which again is not the focus today. But if you have any question about it, I mean, I can try to give you like short descriptions if this is not sufficiently clear. Okay, during runtime, the meter will log statistics about the network, okay? As the network evolves, it will log statistics, but also like checkpoints will be taken of the state of the network. So if the experiment crashes for any reason, because somebody like unplugged your workstation, or just for some other reason you exhausted like your time quantum on a supercomputer and the experiment crashes, you don't lose everything, okay? And the logbook will take care, again, remember, the logbook mediates the interaction between your Python space and the disk, okay? So the logbook will write stuff to the logs about this experiment. And once the experiment finishes, the structures are destroyed, the flow is shut down, and it's finished, okay? Okay, so an overview for users, actions that you should do before running Python main.py configure or Python main.py train is you should create a problem sub-package. And remember, the data usually does not prepare itself. I mean, for the tutorial that we provided you, the data is automatically downloaded from PyTorch because Cypher10 is quite small, and the PyTorch developers provided us a way to do it seamlessly. But in general, you have to prepare this data. Then remember, you have to create a topology sub-package. This will create the so-called working files. So all the content of, almost all the content of the topology package is called like working files. So all the .py files, the modules, plus the JSON configuration files are called working files in the jargon of QuantLab. And these you have to write them yourself, because these, I mean, again, this is where the designer effort lies, okay? So you have to write the data preprocessing, the data loading, the network definition, the output post-processing, and And also remember to configure the configuration file, because, for example, in some cases, you might want to, the configuration essentially tells you, you can tell QuantLab, instead of trying to use, for example, the vanilla stochastic gradient descent algorithm, try to use the Adam optimizer. And this you can do in one line I will show you later in configuration file. And so also here you have to, let's say, specify the last details about your system, and then you can finally run the configure flow and the training flow. Of course, if you want to try out different hyperparameters, you have again to edit the configuration file, but you will be using the same network definition, post-processing and pre-processing that you wrote before. So you just need to edit your configuration file and iterate, okay? In case you want to change the topology, instead you have to go and create a new topology subpackage and repeat all the process. Okay, all clear? Any question? How many people have remained? By myself? Okay. Okay, so let's conclude this section. Now we will move on to the quantized neural networks specific section. Okay, so quantized neural networks are networks that, instead of using floating point operands, as is normal for general deep neural networks, they use limited precision operands, be it the weights, so specific parameters, or the feature maps, okay? This is a choice of design. It also depends a lot on the hardware on which you plan to execute your network. So actually, whereas normal deep learning, usually data scientists and machine learning specialists, they do it without take care for the underlying platform, because they assume that it will run on platform that support FP32 or FP16 arithmetic. When you develop QNNs, you already should have, at least you should be aware of what platform will run your network, because this is exactly the reason. You have to be sure that the operations that the platform supports operations compatible with the format of the data that you're giving into the network. So apart from the previous steps, so data analysis, DNN design and training, graph optimization, code generation, compilation, in between, when you do quantization, you do what is called fake quantization, okay? This is like, fake quantization is called like that because actually you're executing still, you train a network which uses a limited range, a very specific range of floating point numbers, okay? But you will be able to transform it to execute on purely integer or anyway, like very simplified arithmetic, okay? But at training time, you're still using floating point arithmetic. And by using a constrained subset of floating point numbers, we say that this is like fake quantized, okay? So you have this step, which is float to fake conversion, where you take a floating point network and you make it like you constrain like its floating point numbers to take value in specific sets. And then you have the fake to true conversion. The fake to true conversion is when you take these constrained floating point and you turn them actually into integer operands by preserving as much as possible the functional equivalence between the input program and the program that you will like optimize and compile for your platform. You have two flavors of quantization algorithm for neural networks. The first one is post-training quantization. As the name says, it takes a network which has already been trained in floating point. It applies some float to fake transformation. And for example, I don't know, an example might be you take the distribution of the weights and you bin them in a limited number of bins by using k-nearest neighbors, KNN algorithm, okay? In other cases, you might want to do something more aware because this approach like usually destroys a little bit of the performance of the statistical accuracy. So what you do is you insert a fine-tuning step, still in floating point on the fake quantized network this time, and you do some adjustment on your learned parameter, constraint floating point parameters. When you use very constrained quantized spaces for your operands. For example, instead of using, let's say, all int 8 or int 4. So instead of 16 or 256 levels, you want to use just ternary networks or 2 bits networks. So 3-4 values per operand. In these cases, post-training quantization, as for now, it has not shown to work well. The performance, even for simple classification tasks, drop by significant margin. And by significant, it was like more than 20%, 30% on Cypher10 at least. Which is like a 10 class classification problem. So this is like a huge drop. So what we do in this case, instead of using post-training quantization, you see that we no longer train the network here. What we do is doing all the training using fake quantized network in what is called quantization-aware training, okay? So this is like the other flavor of quantization algorithm. And today in the exercises, we will focus on exactly this kind of stack on quantization-aware training algorithm. Okay. Today we will not deal with these steps, so no graph optimization, no code generation. Okay, we will not actually generate code for a running demo on a real on real metal, real piece of hardware. We will focus instead on these steps, which are the more trickier, the trickier to master when it comes to quantization, at least for me. Okay, so how does QuantLab deal with quantization? It has the QuantLib package, which can also be you can also download it and install it as a standalone Python package, but it can be used like it was born inside QuantLab. We actually factored it out just recently, so it actually like works seamlessly with QuantLab for the moment. What is the structure of the QuantLib package? The QuantLib package contains mostly 3 sub-packages: algorithms, editing, and backends. And to understand their purpose, we need again to have a look at the stack of deep learning development for quantization-aware trained QNNs. The float to fake conversion, it is performed using the tree traversal and leaf replacement tools exposed by the lightweight package, which is a one of the 2 sub-packages in the editing package. The quantization-aware training can be done by using algorithms implemented in the sub-packages of the algorithms package. Instead, fake-to-true conversion as general-purpose capabilities provided by the graphs, editing.graphs sub-package. And today we will focus on this, whereas like in the end, like some fake-to-true conversions actually, remember, you have to be aware of the platform. So you actually, to do this stuff, you need to be aware of the so-called backends. So the accelerators or devices that you are targeting when training your neural network. So some functionalities will be developed in the context of the backends package. Okay, so this is also reflected. I mean, how does QuantLab manage quantization inside, for example, is a hierarchy of systems and namespace that we saw before? It adds a quantized sub-package inside each topology package, okay? Where you define all the scripts related to quantization, which we call quantization recipes and controller creators. But we will see later how this works. So again, we take the typical iteration of QuantLab usage, and when we want to use it to train QNNs, we need to take into account these additional steps. So when creating topology package, we need to write quantization recipes and controller creators in the quantized namespace. Then after the network is trained, okay, and we found like good performance, we need to perform fake-to-true conversion. And finally, we can generate code for the platform. At this moment, I have to warn you that this is not this has not been automated yet. Okay, so we're still doing it in a kind of manual way. It's on development, and okay. And in fact, like now, I will tell you what you can find in QuantLab right now and what you will find in hopefully the near future, because we are working on it. So existing features, okay, we've seen configuration-based training flows. We support multi-GPU and multi-process trainings. It is integrated with TensorBoard, so we can nicely visualize the results of your experiment. We support float to fake and fake to true conversion, and we have, as for now, like already 5-6 algorithms, quantization-aware training algorithms for neural network, training QNNs. Planned features, it's already there, but I still have to finish testing it. It's data network initialization seeding. So for experiment replicability, this is especially important for people that want to do cross-validation, because also QuantLab supports cross-validation experiments, and you just need to configure it at configuration time. Code generation, like in a more automatic and consistent way that is done right now. Miguel will be working on post-training quantization, which like it will be very nice to have, like it's a feature that we will invest some effort into. Of course, more quantization-aware training algorithms. I'm actively also working on this. And Georg is working towards supporting mixed precision, which is already like at a good stage, but of course, like there is still something that needs to be done to automate and make it like clean. Okay, again, okay, so we are almost got to the point of the first break. If you have any question about this second part, so QuantLab and QuantLib, feel free to ask. Killed everybody. Nobody? Okay, so if you are okay with that, I would suggest we take 10 minutes break. So 10:10, we proceed with the next part, which will deal with the tree traversal, leaf replacement, and the demo of QuantLab.
Thank you.
Thank you. Can I pause the recording?
Yes, you can. The break button.
Pause share.
Oh, it's a share.
No, this is pause share. Pause recording. Zoom recording. Okay, so here we are. We are ready to move on with the first session, the first part, including an hands-on session. Okay. Can you hear me?
Yes.
Okay, good. I hope that people are back. Otherwise, okay, we'll just like go and then let's see. Okay. So graph editing in QuantLib. By graph editing, what do we mean? We mean all the graph manipulation techniques that are necessary to perform quantization. So we will actually constrain the manipulations of graphs that are manipulation to graphs that are computational graphs, or anyway graphs that represent entities exposed by the PyTorch framework. Because remember, PyTorch, QuantLab and QuantLib work on top of PyTorch. They do not yet support TensorFlow or other frameworks. So we will focus on PyTorch. So the two main classes of transformations that we will talk of are tree traversal and leaf replacement. So, and algebraic graph rewriting. We will start in this session talking about tree traversal and leaf replacement, because before like using quantization-aware training, we need a fake quantized network supporting the desired quantization-aware training algorithm. So we will do what is called a float to fake conversion. So first, a little bit of terminology. So a tree is a directed graph that if you make it undirected, so if you essentially also, if you have an arrow pointing from one node to the other, you also add the arrow going from the second node to the first, then this graph is acyclic. So you cannot like find loops inside your graph. And it also has just one component. And a rooted tree is a tree where one node is the root and all the directed edges follow, have a natural orientation depending on the shortest path going to them from the root, or from them to the root. So if you imagine to start from the root and navigating a tree, like down its branches, like this exactly like it's called a tree. So we see like this growing process, and the terminal nodes, so the nodes that have no arcs, outgoing arcs, we call them leaves. Okay. Tree traversal is the process by which we start from a root and we go to leaves, and we'll enumerate and have handles on all the leaves at the end. And leaf replacement instead is the process by which we take one of such leaf and we either replace it with a leaf or with another tree whose root takes the place of the replaced leaf. Okay, so this is a graph that is also a tree. Okay. This is not a computational graph, okay, because we have no, the moment we have no, it does not satisfy necessarily the constraint that each memory node has just like one outgoing, one incoming edge. But in general, like the purpose of this representation, of a tree representation, is when you have to describe hierarchies. And this is exactly how PyTorch modules define hierarchies, okay? They define network objects by defining hierarchies, by grouping together semantically related and functionally related modules. The purpose is that for performing like successful leaf replacement, we first need to traverse the tree. So imagine that the arcs pointed towards the root. Okay, so the uppermost node is called the root. We reverse the arcs and we start traversing it. And in this case, we show a so-called depth first tree traversal. So we go to the first node, the first child of the root. And then instead of moving to his siblings, so to the node in the center, we start traversing the children of this first node. So this we discover, and it's a leaf because it has no descendants. This is discovered, and since it has no descendants, it's also a leaf. Now we move to this node, okay, because we cannot go longer deep along this branch of the tree. So we change branch, and again, we take this branch and we see that, okay, this is no descendant, so this is a leaf. This is not a leaf because it has descendants. So the first descendant is this, and again this. So at this point, I have discovered all the leaves of the graph. Now, leaf replacement, okay, so if we've done tree traversal, we have discovered all the leaves. Imagine that we want to replace this leaf for some reason. Later we will show an example of why we want to replace this. How can we do it? Okay, we detach it and we just plug in a subtree in this case, okay? And essentially we have grown the tree. Okay, so now we move to the exercises part. So for this, like people who have downloaded and installed the repo, they can follow along by going to the examples folder. Okay, and you will find 4 folders. And what we are interested for now, first, we start by opening the Anna notebook. You should open, if you want to do the exercises, the version student. Okay. Okay, so I will zoom in and I will try to keep people that have not downloaded like the notebook and the repo up to speed, although like this is maybe too much. Okay. So again, here I go again through the something that I've already also presented in the previous slides. Okay. Again, the structure of the QuantLib package. For this moment for this part of the workshop, we will focus on this part of the package. So quantlib.editing.lightweight, which contains the functionalities to do float to fake conversions. Okay. Okay, let's start. Okay, the target of this notebook will be converting a ternary neural network, in this case a VGG8 topology, to process CIFAR images with the additive noise annealing, or ANA for short, algorithm, targeting the accelerator QT, which was developed by one of our PhDs, Moritz, which should also be attending the workshop, I think. Okay, so let's start by defining a PyTorch network. So the first thing I do, this is Python code, we import these namespaces from the PyTorch collection of packages. Okay, and for this moment out these configs here. It's just functional for here, but it's not critical. So let's see how do we create a network in PyTorch, how we define a network. Remember that PyTorch uses dynamically created computational graphs. So in PyTorch, we have modules, okay, the basic components for describing networks is the NN.module, okay? And these modules are of two kinds. We can call them basic modules, which essentially perform real functional transformations, and containers, where containers actually group together semantically and functionally related modules, which can be either basic modules or recursively other containers. Okay. Usually, an object of class NN module, like when you define a network, these objects, objects of this class, will become container modules. Okay. And in this case, you see here that you define like 4 main blocks, 4 main children of this module. One is called pilot, one is called features, one is called edge pool, and one is called classifier. If you go looking into what pilot is, okay, so these are all modules, okay? These 4 are all modules. Let's look at what is pilot. And pilot is created by this method self.makePilot. And you see that what this method here returns is an n.sequential. And this n.sequential is a container module, okay? This container contains these 3 modules. These are basic modules, which are a convolutional transformation, a batch normalization, and a nonlinearity called ReLU, okay, rectified linear unit. Similarly, the construction of the make features is more involved because you have to follow the loop of traversing this list of describing the configuration, but it's still, the output is still a container, okay, a sequential. Instead, edge pool is itself a basic module, okay? Whereas classifier is make classifier, and as you can guess, like it's similar to the other make methods, and it creates like a container, a sequential container where all these basic modules will be executed one after the other. Instead, at the runtime, like PyTorch will, when we will use the PyTorch network, essentially when you trigger the call to this forward, okay, this forward method. And if you see here, it will get in input a memory array, okay? So a torch, which is called a torch tensor. This is like a data structure in PyTorch that wraps arrays, which are like the container of the data. This will be fed in input to the pilot, and pilot will, like in sequence, call all these 3 transformations and output another array. So this is homonymous to this symbol, but is actually a different array, okay? And this is fed now to this, and this sequence of transformations is applied and returns another array. this array is fed to fspool, which is a basic module. So this directly outputs the output of this operation. In this case, we have a structural transformation, which is made so that the shape of the array, okay, of the memory region where the data has been written to by fspool, can be read by the modules defining classifier. So this is just like a structural transformation, okay? There is also a comment to a difference between a similar command and, I mean, if you want to dig in, like this is the starting point. Okay, so just to give you an idea of what this means, let me go back to the presentation here. Because if you remember here, I showed you how PyTorch creates. So you see that here are like these 4 blocks, okay? And this is analogous to what you do here, because in fact, in the constructor method, okay, in the init, I promise that in the init, these operation supernodes are defined explicitly. And in fact, like here, they are defined. So these are blocks. But I still don't know what is the relationship with them. I mean, only the programmer can tell what is the dependency relationships between these blocks. Instead, during the forward, by like writing down sequentially the sequence of instruction, we tell how this should evolve. Like, so you see here, we define in the forward call. I mean, here I say implicitly because like this is like in the mind of the programmer until like this is written down in the forward call. And you see that here, this is X, this is like X after pilot, X after features, and so on, okay? And this is what happens here. Okay, so we, sorry, I was on the wrong tab. Okay, we create we define the network, and then we create an object of this class, okay? So this network is a floating point network. I mean, this network has no notion of quantization. So the whole point now is being able to replace each module here, I mean, or at least some of the modules here, with counterparts that support quantization-aware training, okay? So, because to quantize this network with quantization-aware training, we need the NN modules that support this quantization-aware training. And not all of these like exotic or very like frontier training algorithms are supported natively by PyTorch. This is why QuantLab was born, to extend the functionality of PyTorch. Okay. So in this case, in this tutorial, we will use again the additive noise annealing algorithm. And to get an idea of how this algorithm works, you see that we need to import these unactivations. For example, we import like QuantLib algorithms, okay, this namespace, and we see that this module, this is like a specific NN module, which is defined in the ANA namespace. And to create it, we need to tell how the output of this module will be quantized. So in this case, it will be quantized using like 2 bits. So it will, at most 4 values, it will be signed. So it will be used, instead of using 0, 1, 2, 3, it will be used -2, -1, 0, and 1. And by balanced, I just tell it, okay, I want the same number of values on the left and on the right of 0. So just ignore the -2. So this will just use -1, 0, and 1. And epsilon is essentially how these values are actually distant from each other. Like, will they be -1, 0, 1? Or I want them to be -0.5, 0, and 0.5. Because remember, fake quantization does not enforce you to use integers. Actually, its whole purpose is to use constrained ranges of floats to ease learning, or at least this is like the accepted state of things, even though we are religiously believing it more than actually checking that if this is actually necessary, or at least this holds for me, that like you really need fake quantization, but let's assume that this like is really needed, and because all the world is doing like this. The point is, this is used to regulate the distance between your quantization levels. So here you have the inputs, okay? You generate a fake range of inputs, and we show here how the ANA algorithms achieves quantization. So you see that here I give a keyword normal, because essentially how this works is by adding some noise to the inputs of the activation and taking the expectation under this distribution of noise, you will get the differentiable function, because like ultimately you want something like this, okay, which is like the derivative here is always 0, but for the jumps where Gianpaolo, forgive me, it is infinite, okay. We go there by annealing the noise, so by concentrating the noise. Instead of having a widespread Gaussian, we're going to anneal it to restrict, like to make it like having a very small variance. And if you see here, what happens is that you see that what I do here is I reduce the noise, okay? So I go from a variance of standard deviation of 0.8, and I go down to 0.0, okay? And this is like the standard deviation, okay? Which is square, but of course, like this is smaller. This is like a monotone increasing function. So if this decreases too. And you can see that here, by reducing the noise, I slowly anneal the function to this. Okay? So how can we take a floating point PyTorch object and turn it into a fake quantized PyTorch object? This is why we need the QuantLib editing lightweight namespace. So we import QLW. Okay. So before we move on to the lightweight, like through this like part of the tutorial, we pause this notebook and we go back to the graph editing examples folder. You can open the graph editing student.py. Actually, I should also open it, so otherwise like solutions are spoiled, but I think most of you have already looked at them, or at least I would have done that. So, okay, because in this part, we abstract away from all the details required in QuantLab, okay, because they of course depend also on all the PyTorch specific details and stuff that are defined by the PyTorch framework. And I tried in this notebook to abstract away some details in order for you to focus on understanding what's going on, okay? So in the first part of the notebook, in these cells, I define some functions that are actually mostly important for rendering, okay? So these, like I define, apart from these, which I define enumerated, so I told you before, there are like container and basic kind of leaves, okay? There are these two enumerations. These I tell you, okay, there are container modules and basic modules, and there are, and in more detail, I want to mimic PyTorch, so I say there are container modules, there are linear operations, pooling operations, and normalization operations. So here I just define some functionality that will be useful to like display figures that will be, hopefully they will give you some more intuition. What we go down here is that we have these cells, so this third cell of code. You see here I've defined a class module, which is intended to mimic the ANA module. Like the class that we used here to define networks. So the most important things that need to be here are the type, okay? So at creation, you can pass children. So each module can have children in this case. You can pass a name, okay, which can even be none. You can even like pass an anonymous name. Anonymous, yeah, the module can be anonymous. And then it will have this attribute name children. So at creation, you see that you call this register children. And what this does is it takes like the children argument that you pass to it, and it will look how many of the children have a name. The convention that it accepts is that either you give a name to all the children or to none of them. And if all of them have a name, then of course, named children will be a dictionary that pairs the name of the module with the object itself. And otherwise, I just name them, giving them a number, a string representing a decimal literal. Okay, and then once I create this dictionary, I save a pointer to it in the name children attribute. Okay. I could have used update there. It would have been nicer. Okay, anyways. Then I define two children classes, container and basic. So container, you see that I pass a children argument. Okay, it can still be anonymous. But the important thing is that children, I have to pass it non-empty, because otherwise what container is it? Okay. And it automatically be assigned the type node type container. Instead, basic modules, they are passed no children argument. So you see that I create, of course, an empty list because they're basic. Okay, there should be leaves in the tree, the hierarchy. But I have to specify a module type, which can be nonlinear, which can be, I should actually assert it that it is like not a container, but okay. Okay, and then I create a network which is similar in structure to the VGG that we defined in the ANA notebook. Okay, so I define a pilot. Okay, so I call this module, this container module pilot, and it contains a sequence of linear, normalization, linear, and pooling. Again, features it's similar. Okay, and I name it features. I create an object named pooling, and I call it pooling. Okay, classifier name classifier, and finally, I wrap all of this into a single container, which contains pilot, features, pooling, and classifier. So even like the fact that this pooling is actually a basic node is actually made to mimic exactly almost one-to-one what's happening in the ANA notebook. Okay, so as a first exercise, your problem will be to traverse the tree. Okay, what I want to return is returning. So you see that what I return is an object of type network X directed graph. So I pass to it a network. Okay, so this module. Okay, that I've just created. I can pass this net, which is a module, because since it's a container, it is also a module because it's a child class. We need to traverse it, okay, and we need to return a tree. So we need to with this G is a network XD graph, which in the beginning, in the first like call to traverse tree is empty, but as long as the more we go down, the deeper it will grow. So the point is that we can add nodes by using G add node, and you can add edges using g.addEdge. And you have to feed as inputs the string, which is the name of the parent, and the string that is the name of the child. Okay. Is it, I mean, I think that like 5 minutes, 10 minutes, I don't know. You tell me if you, how many of you are interested in making the exercise, in attempting to solving the exercise? Because I can actually also like just go on and just like describe what's happening. But of course, if someone is interested in doing the exercise, I think we can. I made this assumption that people would have wanted to do exercises, but maybe not. So you tell me. Guys?
I think it's a good exercise.
Okay.
Let's do it.
Okay, then just 10 minutes. I remain here. If you have any question, feel free to ask. Oh, one thing. Notice like here, a module path. Okay, so each name of a new node should be a module path, and the module path is a string of dot-separated module names. So the name of a node that you're going to add should be a different name. Okay, if two modules, okay, let's suppose the two modules have the same child, which is named 0, decimal letter 0. Network X, when you add these nodes, it will consider them to be the same because they have the same name. Instead, if you create the name of the node by concatenating the names of the traversed nodes using dots, you are sure that the names won't clash. you need any help, let me know. Okay. Do you want some more minutes, or you want me to proceed with the solution?
I have one question, or more of a note, I guess.
Yes.
If you do this with not these more abstracted sort of, container and modules, which don't really do anything, which are just like labels, like if you have a network and you use this type of logic to traverse the tree, it will only work if every node is either a container or a functional node, right?
Yes.
You should not mix them both.
Actually, no, because it is the purpose of the. I mean, you mean in a container you cannot mix both?
I mean, in a container you shouldn't have additional logic which is not encapsulated again in a submodule.
You can, in principle,
but it will not end up in this type of representation that we construct here, right? Because when we see that a module has children, oh, never mind, sorry, yeah, no,
I think it is independent.
I made a thinking mistake.
Don't worry. Okay, let's start by coding. So the first thing is computing the full name of the child, okay? So remember that we are traversing a tree, and I told you that if we gave the same name, network X will make the names clash, okay? If it finds the same module name by performing traversing two different paths. And this is important because at the moment, QuantLib relies a lot on the network X library for network manipulation, okay? So this we need to take into account. I mean, and it's good to learn that these clashes can happen because it can lead to some errors, especially debugging some errors in the graph rewriting rules is not so easy if you're not aware of these kind of things. So let's go like module name. 1 second. Okay, so full name. So we have two options. So if the name of the parent is nothing, we don't want, then full name will be sorry. If the parent is empty, then the full name will be just the child name, because I don't want to append the dot. Else, the full name will be join. I will join module name with child name. Okay. Then what I add is add node. Okay. And I add node full name. I want also to add type information, and I handle on, sorry, here is like child module. okay, because I want to add the type information about the child. And then I want to add an arc going, pointing from the child to the parent. And finally, I need to call to make the recursive code. So traverse 3, module is the child, module name is full name, and G is the graph itself. Okay, so now what the new type is not defined. There is some cell that I missed execution. Wow. Why this has disappeared? Okay, there is this missing. Okay, I don't know how it could have. No, it's here. It's just okay. Maybe okay. Okay, that's executed. Let's see. Okay, now we're going to use the rendering functions that I defined in the previous cells, like in the first cells, to see if this works. And of course, render format. Georg, sorry, can you again?
What can I do?
The render format that was inserted yesterday.
It's at the very end of this line, exactly.
But what is it? Render format like this?
You have to check, but I mean this worked just before, right?
Yes, I tested this.
It's in the function one above. One cell above.
No, it's here. It has not been. Okay, so this is render format. This should be a string. And
you're gonna have to default here.
What?
You have to give a default because the previous arguments have a default.
But what?
Just make it SVG or so.
Yes, but here the dgraph, I have to pass here render format.
Yes, but it's format. It's just format.
Okay. So now we have traversed the tree. Thanks. This frame, open a new tab. So you see that if we traverse the tree correctly, you should see like this picture here. So you have the root, which is the network, the whole network. And then it has two containers, pilot and features, a basic module, pooling, and another container classifier, okay? And below, since we didn't give names to the modules in the containers, you see that they have been labeled by decimal literal strings. 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3. Instead, in the second rendering, I highlight the node types. So in this case, you see that nodes of type linear are depicted in blue, nodes of type container are gray, nodes of type normalization are yellow, nodes of type nonlinear are green, and nodes of type pooling are red. Okay? So we have fully traversed the tree, okay, and we have handles on all of its leaves. All clear? I hope so. Nobody is commenting, so I don't know.
Yes.
Okay, perfect. Very good. So let's proceed. Now that we have traversed the tree, we have to go on with leaf replacement. Okay, and to do leaf replacement, usually remember that our ultimate goal is doing it for real PyTorch networks. Okay, and what we are interested in is mostly like node types and node names, because what you will do, you will say, okay, I have a network architecture, network topology, and I want to fake quantize just the feature extraction, okay? Just the convolutional layers, okay? I don't want to quantize the classifier part, for example. And then maybe you want to quantize just the weights. You don't want to quantize the features. So in this case, you might want to replace just the convolutional nodes in the feature extraction, which in the case of this, let's say, toy example, is composed by pilot and features, okay? So to do this, we create like these function, okay, this structure, we have a structure which is called leaf node, which has two things: a path, which will allow us to filter nodes by name, and a module, which will allow us to filter the list by the type, okay? So in this get nodes list, we see that there is tree, okay, we have a tree, and since we have created the tree, because we have traversed the tree, okay, we can create a list of leaf nodes by looking, this is like network X syntax. So this nx.getNode attributes extracts a dictionary, because each node in T at creation, if we go in this code, you see that at creation of each, when you do add node, we add this type and module keyword. This creator method actually adds a dictionary to each node. And in this case, we want to extract for each node, we want to extract the module value. So we have this, we use this syntax to get this dictionary and then loop through its items. And since the nodes in a graph like have, I mean, this was pointing, the nodes were created by pointing upwards. Then if you see here in the prints, I revert the direction of the arcs. But remember that the structure, the arcs are pointing from the bottom of the hierarchy to the top of the hierarchy. So the leaf nodes are those nodes where which have no predecessors, okay? So in network X syntax, if I take a graph and I look for the predecessors of a specific node, this returns an iterator over the predecessors. So if I make a list out of it, I can compute the length. And if this list is empty, I know that the nodes are leaves, okay? And you see that if I print out all the leaf nodes, they will have a path and the type, which in this case is just an enumerator that we defined in the first cell. Then let's move on with the replacement. Okay, in this case, I did not make it an exercise. So let's look at the logic of replacement. So the logic of a replacement, I mean, we're not going to filter this by names and type, because this I will show you in a minute, like in how this is done in QuantLab. But to replace a node, you need three things. You need the network, okay, itself. You need the path from the root of the network representation down to the module that you want to replace. And you want the new module, the one that you want to replace it with. The logic is the following. First, we traverse the tree. Okay, we have to traverse the tree down to the module that we want to replace. So remember that the path is dot separated. So what we do is we try to split the string, which is the path, along dots in two parts. This split along the argument with argument, second argument 1, tells Python to take a string, look scanning from left to right for the first dot, split the string in 2 pieces. The first piece is let's say the name of the child that I'm currently traversing, and the rest is the subpath. So the remaining part of the path that I yet have to take. And once if there is actually this part, I make the recursive call. So I traverse the tree along this path. Instead, once I reach the leaf, this action will fail because it finds no dot, so it cannot split the string. Okay, so it will cast a value error. In this case, the child name is the path itself. And I can directly look through the children of the current module, okay, look for the child name, and this should be a basic module. Because remember, if I want to replace a leaf, and a leaf by definition in our system is a basic operation, a basic module. Then what I do is I just use the dictionary of the name children, okay, in the module, in our module, to replace the old module, which had the name child name, with the new module, which was provided as an argument and was like passed forward down the recursive call. Okay. This is the function. Let's see it in action. So in this case, I want to replace, okay, I want to replace just nodes of type linear in all the network. Okay, so I filter the list of nodes by type. Okay, and each node will be replaced by a new container. Okay, I created a new, notice that I created a new anytime, because otherwise, if I created before, all the modules will be replaced by the same instance of the module, which is not the intended behavior. We want to replace each leaf with a new instance, maybe built in the same structural way, but it should be a different instance, as much as the leaves are different leaves. So in this case, I create a container containing 2 nodes, a sequence of nonlinear and linear. Okay, this is just a mock-up. I mean, we use this something similar in one of our transformations, but in the real Quant Lab. But this is just a mock-up. Okay, so in this case, I will just replace a leaf with a small container, and I will call it on all the nodes. This should have done it. Let's see if we did it correctly. It seems that it worked, right? Because if we looked at the previous thing, the blue nodes were the first of the first container, the first and the fourth, the fifth of the second container, and the first and the last of the last container. And indeed, it seems that we replaced the correct nodes, right? So at the beginning, we had, can we go away, please? We had this, okay? And now we have this. Again, remember that each linear node has been replaced by the container of a linear, a nonlinear, and a linear. And in fact, this is like nonlinear, linear, nonlinear, linear, nonlinear, linear, and all the replaced leaves have become containers themselves. Okay? All clear? All good?
Just one comment.
Yes.
So because before you were talking about computational graphs, and so here the graph has a different meaning, right?
Exactly, exactly.
The graph represents just the structure of your module.
Exactly. This is a hierarchical structure, a hierarchical representation of how PyTorch represents PyTorch NN modules, and how you build network objects in PyTorch. But here we are not yet to the level of computational graphs. Yes.
And so you need the graph representation only to find the modules which you want to replace.
You need which representation, sorry?
The graph representation.
Sorry, there was an interference again. I cannot hear you.
You need the graph representation only to find the module that you want to replace in your network.
Yes, yes.
And not
no, it has nothing to do with
how link the module together.
No. Exactly. This is just, let's say, something that simplifies the editing of your PyTorch object, but we are not yet down to the level of computational graph. All clear? see the number of participants decreasing, so probably people are dying, but okay. Okay, let's go back to QuantLib. How this tree traversal and leaf replacement is done in QuantLib. In QuantLib, you do this tree traversal is performed automatically by the so-called lightweight graph. So lightweight graph performs this tree traversal, okay, dynamically. The only thing that it stores, though, is a list called nodes list. Actually, here I say that it's a private, but actually it's made a property, so it's actually accessible publicly, just in read-only mode, okay? So a lightweight graph performs tree traversal, giving a network PyTorch object, okay? So at creation, the creator method of a lightweight graph is given a network PyTorch object, and it will perform tree traversal, building a nodes list. A nodes list contains this structure of type lightweight node. And lightweight nodes are exactly the thing that we called leaf node in the toy example of the graph editing notebook. Because if you see, there is the show nodes list, okay, when you wrap a network, a PyTorch network inside a lightweight graph, it will do the tree traversal and save the structure. And then we can use the show nodes list to print out, you see, all the names. This is the real VGG8 network that we built. And this is the list of types of the modules. Okay? Then we want to select the nodes to be replaced. Okay? And how do we, so we have to select them and we have to replace them. So selection is done by filtering these nodes. Filtering these nodes can be done with two types of filters. You have basic filters, again, and composed filters, which is, I mean, it resonates with the distinction between container and basic, but is actually distinct in the sense that basic filters take, I mean, all the filters, they can input a list of lightweight nodes. Basic filters just look for the names or the types of the modules. So at creation, type filters or name filters, I mean, type filters are passed a class. So in this case, the definition of an N comes to D. You see that QuantLib lightweight rules filters type filter. Instead, name filters are given a string and they will match all the lightweight node whose name matches a regular expression defined like so. Okay? So you pass an regular expression and the name filter will output a list of nodes that whose name matches this regular expression. Then you can compose filters using logical operators. You can use the negation, using the minus filter, okay, the notation is minus filter, or you can use the conjunction, so the and, or disjunction, the or, which are available either in binary or variadic form. So you can chain multiple, like you can create these filters with multiple type filters and or name filters at the same time. So you can use set notation in Python, okay? So in this case, let's suppose that I want to get all the convolutional field, the 2D, the convolution 2D PyTorch modules that live inside the pilot or features container, then sequentials. So I define this by saying pilot or features, and these will just select the nodes in pilot or feature like parts of the network. And then I want, but they want only the convolution, the 2D convolutions. So I have to end this composed filter with this type filter. And in fact, if I apply this filter, you see, to give it an input, the lightweight graph nodes list, remember that lightweight graph wrapped the network, and I print out, you see that it returns just the modules that I want. Okay, so, okay. At this point, I we need to replace the nodes. So, and the logic of replacement in QuantLib is performed by the so-called lightweight rules. Lightweight rules are objects defined in this way. So to define a lightweight rule, you have two parts. You have the filter, okay? But the filter will be passed, since this depends on the network itself, because names of modules can change. If you change network, the names will almost always like change. So I leave it as an argument. A filter is passed as an argument. But then instead, what instead is stable, independently of the network, is usually the replacement action. The replacement action is performed on a module, okay, and it returns what we called in the toy example the new module, okay. So the new module, you have to create it, in this case, depending like on the parameters of the floating point module, but then you pass all the hyperparameters needed by the creator of this AnaConv2D fake quantized module to actually be a fake quantized module. So this function is like just a function that takes a module, a floating point module, and returns a fake quantized version of the module. A fake quantized version that depends possibly on the quantization-aware algorithm that you want to use. And then in the creation of a rule, of a lightweight rule, you can actually leave it open to specify the hyperparameters, okay, because the hyperparameters you might depend on the network that you want to quantize. For example, you might want to quantize a network with the same algorithm, but at 8 bits instead of, let's say, 2 bits, okay? So you want this also to remain open so that you can recycle this rule for multiple networks and in multiple contexts. These two parameters, usually we fold them by using the functional programming tools offered by the functools package of Python. In this case, we use carrying, where you just say, okay, we create a function that just takes these two arguments and we instantiate this general function with these specific values of the hyperparameter, fake quantization hyperparameters. So that this function that you pass to the constructor of the parent class will actually be a function that just takes a module and returns a module. These parameters will be fixed. So when you create this rule, what you do is actually just passing the filter that will look for the application points of the replacement and the upper parameters to instantiate this, let's say, core function here. Okay? Okay. So some manipulations are not so trivial to implement. Okay. So what we do also in QuantLib is providing you with the so-called lightweight editor. The lightweight editor is a wrapper for that you can, where you can execute inside commands safely, so replacement safely, in a way that you can also revert and unapply. So to do it like this, there is this concept of a session, an editing session, and an editing section is essentially a lock that you put on the possibility of modifying or not, of applying or not leaf replacement. To enable the session, you do a startup. To pause the section, you do pause. To resume it, you do resume here. And to finally, we will see how to completely interrupt the session, which will have the effect of confirming the changes that you have made. And so it will not be possible after you shut down an editor to revert the changes to a network. So in this case, you see that we create a network. We select to replace exactly the filters identified by the, we pass the filter that identify the convolutional nodes in the feature extractor, and we pass the hyperparameters for the constructor of the ANA algorithm. Then we resume this, so we remove the lock, we can change the network. We set this rewriting, this lightweight rule, okay, as the current rule of the editor, because the editor has a current rule that he can apply. And then we apply it, okay? And you see how the list of modules is refreshed. So the tree is traversed again. I mean, this is like, has applied already more changes because the notebook has already been run. So start cell, run all above. Okay, we'll get to the point. Okay. So you see here, what it did was replacing what was torch and n modules conv with ANA conv 2D. So this was replaced, this was replaced, this was replaced, replaced, and replaced. Okay? All clear until here? Okay. So now there would be an exercise, but I think the time is not sufficiently much. So I will just like tell you what it does. Like this just replaces linear layers in the classifier with analinear, so fake quantized linear, but the last, and this with the ReLUs with ANA activations. So here you see that we define the filter to exclude the last layer, okay, which has name classifier.6, and here we, in fact, like we create a filter that takes all the nodes but the last, and then we look for those linear layers that are in the classifier, they are linear and they are not the last layer. We create the rule and we replace. These has been all the linear layers have been replaced, so this 1 and 1. And finally, we also replace the activation with an activation. So this is a fake quantized network. We are happy with the transformation, so we shut down. All clear? All good? Okay. Then, to conclude this second part of the workshop, I will show you quickly a demo of QuantLab's capabilities. Okay. So let's look again. You see here the structure. Okay. So this is like my. Can you see my screen?
Yes.
Yes.
Okay. So to run an experiment, first I will show you one thing, that if we open systems, Cipher 10, VGG, okay, I have encoded these changes, okay, like the transformation that I just applied in the notebook, you can also find them here. You see that in a so-called float to fake quantization recipe, I create here like the filters, I define the rules exactly with the same syntax that you find in the notebook, okay? Then I create an editor, I start up, I modify the thing, the network, and by replacing the leaves that I'm interested in, then I shut it down, and I return the quantized network. So the network wrapped by the lightweight graph, but this time it is fake quantized. So let's have a look at how the configuration of an experiment in QuantLab looks like. So the config.json that we looked at the first part of the workshop. This JSON is essentially a dictionary, okay, consisting of several sections. There is the data section, the network section, okay, the training section, including the specification of the quantizer, and the meters section. So it has, okay. Then you see that mostly things are specified in this way. You have an object, okay, so in this case a PyTorch data set. What you have to specify in this case is what preprocessing each image in the data set will undergo. And to specify it, you have to define the class of the transform and the keyword argument. So most of the specifications in QuantLab configurations are specified as class keyword arguments for the constructor method, or function and keyword arguments for that function. This applies to almost every piece of code in here. So for example, here is like loss function. It is of class cross entropy loss, and there's some keyword arguments. The optimizer is the same. There are some parameters that are, for example, this tells you to train the network for 60 epochs. So these are not actually class keyword or function keyword kind of specs, but are more the exception than the rule. And these, again, function keywords, then some functions, so for example, controller, creators, or quantization recipes, they are more involved because, of course, the parameters for the build objects, they are specific to the object that you are creating. So especially for quantization controllers. Okay. So if we look into, let's try to trigger an experiment. Okay, so we do Python main problem cipher 10. I want to train a VGG. So let's start by configuring it. Okay, I'm going to configure an experiment. If we go, it sees that it tells me that it has created something at this path here. Okay. So if I go and look here, you will see that it has now a private configuration file. Okay. And if we go looking what happened into here, you see that something about data, for example, will have been added. So for example, you see that here, cross-validation information has been added. So the number of cross-validation folds and the seed to ensure that if your experiment crashes, the split in training and validation partitions of these like cross-validation experiment will remain consistent. Then okay, since this is like automatically rewritten, you see that this is like has been linearized, so the file will be longer than before. And finally, the experiment, it tells you, okay, the target loss that you have to look for understanding if the model has improved or not is the validation loss, and you have to take a checkpoint every 5 epochs. Okay, in general, you can like print out like what options like the QuantLab offers by looking here. So for example, Python main.py configure. You see that here you can like find, okay, what can I set? Target loss, checkpoint period, number of fold, cross-validation seed, fix the sampler. These like this, we still have to finish like fixing like this, but these will list like all the options that you have for the service, for the QuantLab flow. So now that we have configured the experiment, so on multi-GPU machine, you have to set this because unfortunately with Anna, we are having problems related to the wrapping of controllers and networks inside NN data parallel, which is like for running on multiple GPUs. So if you run with this flag enabled, it should be no problem. So I have to remember, I have to tell you the experiment that I want to train, otherwise it will complain. So, okay, it found experimental unit, cipher 10 data, and it should start. Okay, so now it's taking a long, because it's taking a snapshot, and then you see that it starts. Then we can use TensorBoard to inspect what is happening. Okay, so here you see that we have like several pieces of information about our trainings. So while we were like talking, I ran a second experiment, which is the blue one. You can see like here you have the training loss, which is like going, I mean, this behavior is due to also the ANA algorithm. Same thing also for the validation. To make it easier, I mean, this like would take too much time to explain properly, but let's stop this because I want to show you systems. Let's go back to the config, if I go down, you see that like in the, here I set up some meters. So I told the QuantLab to say, to monitor, for example, the output features of the second, the layer named pilot.2. So this is like an activation, okay? Starting at iteration 0, every 100 iterations, and snapshot the first 4 images, but all the channels. So if we go, for example, in images, you will see that these extract all the feature maps out the first activation, unactivation layer, okay? For images. So you will see like there is like 4 images, and you can see actually how they evolve through time. So you can see like features starting from here, and the, like, of course, also different images, but you can see the evolution of features through time. Okay. I think we got to the end of the second section. So if you have any question, feel free to ask.
I have one question.
Yes.
So I got a bit lost in the point where, because here you are doing quantization-aware training, right?
Yes.
Where do you set? Is in the config where you set what you want to change, or is in the?
What do you mean by you want to change?
I mean, you want to replace some nodes of the graph by the quantized ones. Where do you find that?
So this is determined like here, because in network you have the quantization happens by these recipes in QuantLab. So you have to define these like in this quantized section. Okay, so you have the network section of the config. In the network section, you have the class and the keyword arguments of the basic constructor, but you also might have this quantized section. This is optional.
Yeah.
But if you have it, we go to systems, cipher, VGG, okay? So here you see there is this quantize, okay? And if we go looking into what is exposed into this quantized namespace, you see that from the ANA module, I import this symbol and this symbol, right?
Mm-hmm.
So these symbols, if we go looking into them, right? This is where this symbol is exactly a function that takes in input a network and these 2 keyword arguments, okay? This quantizer spec. And it returns, again, a PyTorch-NN module, okay? But after the conversion, okay? So here, if you go down here, you see that I pass to the quantize. I see, oh, use this symbol, use this function, okay, to convert the network, to do the float to fake conversion, and pass to it these keyword arguments. This for the quantizer spec and this for the noise type.
Mm-hmm. Okay, I see now better. And here you're passing the same function, I mean, the same number of bits for all layers.
Exactly, because this recipe, this depends on the function. This function does it in an homogeneous manner. It's not mixed precision, it's single precision. You could write more complex quantization schemes, okay, where you can pass more complex keyword arguments, for example, to describe mixed precision quantization schemes.
Mm-hmm. Okay. And this function, I mean, this folder quantization within the system, you need to add it there.
Yes,
manually.
It's not created automatically for packages. You have to create it manually, and you have to create these. The important thing is that is a package, and it is namespace. The symbols that you will call from the configuration file, they are defined. Okay. Because otherwise it will complain that this symbol is not found, this symbol is not found.
Yeah, I understand.
Okay, with the difference that the quantization recipe is used by the network assistant when it builds the network. Whereas the controllers, which are the way to control the hyperparameters of the quantization-aware algorithm, are driven by the controllers, okay, these hyperparameters, and this controller is created instead by the training assistant. So you can also specify a quantized section inside the training section of the config, because the role of building the controller is not of the network creator, but of the training, of the assistants in charge of building the abstractions involved in training.
Okay, and these packages we can use out of the box, sort of say. I mean, of course, you will need to change these hyperparameters, but for the function that we saw before, the assistant of the network,
yes,
that's
they will use them seamlessly. I mean, this should take an input, a network plus the keyword arguments, and return a list. It will return a list of QuantLib controllers. If this signature is respected, the tool should work smoothly. Same thing here. If you pass a network that gives takes an input, a network plus these keyword arguments define a configuration, and it returns a fake quantized network, it should still work.
Okay. Thank you.
You're welcome. Thank you for the question. Other questions? No? If no, I would suggest that we take like 5 to 10 minutes break, and then we get back for the last section, which will deal with fake to true conversion, which is like the more involved one, because it will like use more advanced tools of QuantLib. All good? Okay, we'll stop recording. I will pause recording and resume recording. Okay. Can you hear me?
Yes.
Thanks. Okay, hope the other also hear me. Okay, so we have come to the last part of the workshop, okay? And this part will deal with the so-called algebraic graph rewriting, okay, which is like quite delicate topic in the sense that there are many things to be grasped. I will try to give you an intuition about it. We will make an exercise about the graph rewriting, and but I will have to conclude the notebook by just explaining to you the steps, because probably there won't be sufficiently much time. Okay, so now that we have, let's suppose that we have trained our fake quantized network. Okay, what's next after the fake quantized network? We have to transform the network into a format that is compatible with real hardware accelerators or real hardware devices in general. So at this step, we want to create what is the output of the fake to true conversion. The output is a software golden model. So we want, in this case, a PyTorch module, which operates with operands and uses operations that are actually mimicking those that will happen on the end hardware, on the target hardware. So to do this, we need to understand a concept, which is that of graph rewriting. I will jump directly to a slide that gives you an idea of what it means. So what is a graph rewriting rule? A graph rewriting rule is a set of two graphs which share a common subgraph. Okay, so the blue nodes in this case are shared between the two graphs. The blue nodes in this case, but they might actually be more complex graphs, are called a context graph. We will see in a minute why this is called like this. A template graph is the left part, the L term of the rule, is this part here. So this is like a pattern that will be looked into a target graph to replace it with the target operations. Okay, and the template core is the part that is really a graph. Okay, is the subgraph spanned by the nodes inside that are not the nodes of the context graph. Okay, so this is like the nodes, is the subgraph of the template graph that is spanned by the nodes that are not the nodes of the context. Okay. Analogously, we have the replacement graph, okay, which is it's called the R term, okay, the right part of the rule. And the replacement core analogously is defined as the subgraph of the R term induced by the nodes that are not nodes of the context, which in this case are the blue nodes. So the point is that you have, again, an L term, an R term, and a common K term, which is the context, okay? This is a graph rewriting rule. How can we use it to manipulate graphs? Imagine that you have the bottom graph, okay? And you want to replace all the patterns of nodes, like in the upper part, with patterns of node, like in the upper part, like these three nodes, okay? The light blue, light red, and light yellow part, okay? So what we do is we start looking for isomorphic subgraph of the target graph, okay? So we, let's say, go over the target graph, you see, oh, okay, there is a match, you see? Between the target graph has these two nodes, okay? And this is like let's say the part we want to replace. So we match it. So in this case, this is called a match. So when we find a subgraph of the target graph that is structurally identically to the template graph, which remember is the L term of our rule, we say that there has been a match, okay? If we found a match, then the following things happen. Essentially, imagine that the rule, the graph rewriting rule, is like the screenplay of some movie, okay? So, and each node plays a role in this movie. So first, we need to introduce these new characters, okay? These new characters, okay? So this is like the screenplay, and we create these new characters. Then, in the screenplay, we are told that the blue characters are related to the new characters by these like outgoing edges. So what we do is we also replicate this kind of relationship with our factual characters, right? Then what we do is we want to remove from the play like these characters, the old characters, like the L term. So what we do is we unlink the old graph, okay, the old characters, like the actors that are playing those characters, and then we remove these characters, these actors from the play, from the movie, okay, and finally we get like this new graph. So in essence, the blue nodes, okay, this one, the one on the left, and the first blue node in the middle, they are called the interface graph. So the interface is like the actors that play the role that in the screenplay was played by the context graph. The match core, so this is the match core, is the actors that play the characters that in the screenplay are abstracted by these nodes. And these are called the replacement. This is called the replacement graph, the replacement core graph, okay? Then after this rewriting has happened, we move the rule searching for other application points. And we find that here, this is structurally similar, right? This is like the same structurally, but you notice that this node is red, whereas we expected it to be yellow, okay? Because we want to replace this kind of structure only if the nodes are of a certain attribute, okay? They are of a certain type, okay? So we are not willing to replace this substructure if the type do not match, okay? So this is not a match, and we refuse to change the graph, okay? Okay, this is the first concept of graph rewriting. So now, to fully understand like how graph rewriting works, I have prepared like another, I mean, if you continue in the graph editing notebook, we will see that we can like practice on this concept. So first, I define a graph, okay? That if you see here, like this is like a graph. Okay, this is like a graph, this has this pattern, and the nodes have these shapes, like this double fork. Okay, maybe. Okay. Stop zooming, stop zooming. Then we can define let's say the blueprint, the screenplay of the rewriting rule, okay? So this, we see that we build a rule saying that we look for a graph, like the L part of the rule is done by this kind of nodes, and the connectivity is defined. This must be defined by hand because we know what pattern we are looking for, okay? I mean, it's not that I mean, this is not automatic. We need to define the pattern that we're looking for. And we also need to define analogously what is the pattern that we want to replace it with. Okay, so we have this pattern in input and this pattern that we want like to replace the core with. Any question? I know this is quite dense. Long silence. Okay.
Excuse me.
Yes.
Why do we need these kind of replacements? I mean, are we trying to simplify the network that we train?
We are trying to replace the operations that are fake quantized with operations that are true quantized. So, for example, instead of performing multiplication by floating point numbers, we want to represent these multiplications and then quantizing in a floating point domain. We want to let's say, take away the multiplicative factor so that the numbers are actually integer. Let me try to explain this like better. So imagine that you have coefficients that are represented by the number minus 0.3, 0, and 0.3, right? And you multiply this by an integer, okay? What you can do instead is multiply the integer by -1, 0, or 1, okay? And then multiply it by 0.5, okay? Because the range minus 0.5, 0, 0.5 is like the range -1, 0, 1 by the scalar 0.5. Okay, so you're using kind of an arithmetic property where you, instead of doing the multiplication of the floating point scalar by the first number, and then multiplying this number by the other number, you first multiply two integers and then multiply by the floating point number. The hope is that but this like requires you to execute operations in a different order. Okay, so in a computational graph, the order of operations is what determines what is to be executed first. So in one case, you have a graph like, let's say, how can I like describe it? Like it's, so in one case, you might have something like this. Sorry. Something like this. And in another case, you might want something instead like this, or better, like this. Okay, trying to make it like. The purpose is that I want to go from something like this, maybe to something like this, because I'm reordering the operations in a way. Okay? So this is like a transformation that I have to make to change the order of operations. Because in this case, imagine that the yellow is multiplication by a floating point number, but the blue and red are integers. And green is a multiplication. Okay? So in the first case, I have to do integer by float, and then float and integer multiplied together. Okay. In this case, I have integer and integer, which still is integer, and then I multiply by a floating point, but just a single number by floating point, and I don't have to do a multiplication in floating point. Is this sufficiently clear?
Yes, thanks for the explanation.
Welcome. So the point of graph rewriting is, in essence, to provide you tools to reorder operations and or reorder wrappers of operations, because in general, as we will see, we will act on PyTorch modules. So, okay, in general, to write a graph rewriting rule, again, you have to define the blueprint. Okay, so the L term. Then in the L term, you have to specify which part of it is the context graph. Okay, so this you have to specify it by hand. Okay. Again, here you see define context K as subgraph of L. And then we split the two parts. So we say that there is this L minus K component, which is like the core of the template. K is the context. And then there is the edges, the arcs connecting the context to the template core and vice versa. Then you define the replacement core, R minus K, the graph R minus K. And finally, we have to link R minus K again to the context. And this still must be specified by hand, how to link the new replacement to the context, which, remember, the context is share between the template and the replacement. Okay. So now here I prepare like this picture to actually show you better, like something that I've already shown you. But this is like, you see here, there is like in blue, you see the core replacement, the yellow is the context, the golden is the context, the orange is the replacement core. The light blue arrows are the connections between the context and the template core, and the red arrows are the connections between the context and the replacement core, okay? And here instead you see the same graph, but with highlighted type information, okay? So this highlights the type of the operations that the nodes represent. Okay. So the first thing when using graph rewriting is identifying application points. And identifying application points is can be done by using the so-called subgraph isomorphism algorithm, okay, which in NetworkX is implemented by these isomorphisms subpackage. In this case, you give it an input like the target graph, the one on which you are looking for the match, and the template, so the L term of the rule, okay? And it will return a list of isomorphism in this case, okay? What is the problem? Again, you see that here, the first is a good match, right? Because if we compare like the network, let's say the first half of the network, okay, these like the L term, okay, the L term, this is structurally and semantically identical to this, the graph comprised between the two green parts, the two green nodes, okay? Instead, we will find that again, the match is still structurally, wait, please. The second here, these are still the same number of nodes connected in the same way, but you see that here I have a red node, whereas in the pattern, I was looking for a yellow node. So if I go back, here, you will see that at a certain point, I have a mismatch in the types. You see, node 20 in the target graph and the template corresponding node number 8 in L term, they have different types because one is type 3, nonlinear, and the other is type 4, which is, type 3, which is pooling, and the other is type 4, which is a normalization. And in fact, like this is a structural but not semantic match. So what we do when looking for this kind of rewriting rule applications is also looking for the types of the nodes match. I don't know, this exercise is quite simple, so I think we can have a chance at least to see that, I mean, to ensure that you grasp the difference between typed and untyped isomorphisms between graphs. But I mean, really 5 minutes, I think, because I don't want also to, if you have other appointments, like also you want to go to lunch, like I don't want to go over like the deadline of 12:30, but 5 minutes to do the exercise. Anybody interested, or I should go on? How many are going to try to solve the exercise? Is anybody listening?
I think we can go on for this one. We can do later. Okay.
So, okay, in general, like, let's move on. I won't complete it like I mean, I can open like the other version. Okay. So the point is that once that you are able to find application points, these are dictionaries mapping nodes to nodes, because of course, like in graphs, like a match is determined by, okay, this is who is playing the role of whom, like in this like match. What you'd have to do to apply a rewriting rule is first you identify the interface. I mean, given a match, okay, the match, remember, is the graph, the subgraph of G, which it corresponds to the graph L in the rewriting rule. And all the nodes that in L belong to the context, so all the part of the context graph become the interface. Which the interface is the instance of the context, okay? HI, which stands for H minus I, is the difference between the template and the interface of the match. H is the match, okay? So HI stands for H minus I, which is like the match core, which is, let's say, the equivalent, the instance of the template core. JI is the substitute core, so which is the instance of the replacement graph, the replacement core graph. What happens is that first you see that here I create a copy of the replacement, I add it to the graph, but still this is a disconnected component, okay? So what I have to do is gluing the core, the substitute core to the interface graph, which is like tricky to do, but I mean, still it is neat, even though you have to be careful on how to do it. And finally, you can unlink and remove all the old match core. So the nodes that you no longer want. Okay. And if you can see here, you see that like previously, like this graph had blue, yellow, and some other nodes, and now it has exactly the part of the rule that we wanted it to have. Okay. So we have transformed the old graph into this new graph. Okay, so here, like as I showed you like before during the demo, these we assume that the fake quantized network has been trained, so we can upload like the existing checkpoint. In this case, in my case, this exists. For those of you that have also run the notebooks, you should also have a checkpoint by now that you can try to convert. So fake to true conversion in Quant Lab. There are, as I said in the introduction, there are general purpose fake to true conversion capabilities that are provided by the QuantLib editing graphs package. So we import this namespace, but there are also, since this is like really needs to be, you need to know which kind of hardware you're going to execute it on, because remember that the output of this process is a software golden model. We, of course, will end up importing rules that are specific to the platform for which we are converting. So we also import the quantlib.backends namespace. So I want to give you just the highest level like outline possible for how like this fake to true conversion happens, because there are several stages. Some of them are tricky, some of them less tricky. The first one stems from the fact that, remember, our choice was using PyTorch as our, let's say, base development framework, which has the disadvantage of using dynamically built graphs. So when I want to manipulate a graph, I actually need, the first thing I need is a graph. I need a static computational graph, something like fixed that I can analyze and that can transform, like a compiler does, something similar. So this like process of taking a PyTorch network object that, remember, as long as I don't run any data through it, I don't know how the graph is. This process is called tracing, okay? So in tracing, I take a PyTorch network object and I create a just-in-time PyTorch graph. Just-in-time PyTorch graphs are closely related but not identical to ONNX graphs, okay? So for this reason, in QuantLib, we define this ONNX graph structure, which is a wrapper around a network X network object, directed graph, okay? A network X directed graph object, plus some bookkeeping operations. This object is given in input a network, okay, a PyTorch network object, and a dummy input, because we need to pass this input through the network. Okay, you will maybe you don't remember, but we can go quickly back at it. Remember that a dynamically built graph, we need to create like this is like the input. What we do then is, you see, we start like the PyTorch starts building the network because it can push the features through the network and call the operations that will be recorded. And this is exactly what is achieved by ONNX graph. So this ONNX graph takes an input, like, again, a network, a PyTorch network object, and a dummy input. And internally, it will create this traced graph. Remember to set the network to the evaluation mode, because otherwise, I mean, you will trace a different set of operations than those that you will be using at inference. Okay. Writing graph rewriting rules directly for ONNX might, or ONNX-like graphs might be desirable, but for sure it requires bulky networks, because this tracing can easily produce tens, if not hundreds or thousands of nodes between memory and operation nodes and kernel nodes. So what you want to do is instead trying to use this tracing that is like records low-level calls to kernels to rebuild, to build a higher level abstraction of the computational graph, which is like the PyTorch graph, okay? And the PyTorch graph, if you remember, let's try to see here. The PyTorch graph, I mean, we build the network object like this, but the PyTorch graph is something like this. And to build this, we use what is called elevating. So during tracing, all the operations in a PyTorch module are executed under the scope of some of a PyTorch of a sub module of its, right? Because we saw in the second part that PyTorch networks are hierarchical, are trees of modules. So in this example, the tracing, during tracing, the tracer annotated this operation and this operation as being executed under the same PyTorch module, okay? Under the same call and the same forward call to some PyTorch module. So by elevation, we mean this process. We identify, so it's like we glue together like the light blue nodes. If we glue them together, you see that this like arrow going towards this node and then going down to this becomes a loop, because from the blue node you go to the arrow and then from the arrow you go back. So at this point, this transformation creates like this node, which creates like a loop here. So this is no longer a computational graph, because this is not, is directed, but is not acyclic. Okay, it is still bipartite, but not acyclic. So if it's not acyclic, the solution is just to consider this as being absorbed by these two operations, okay, because it is like actually working as a working memory for this like super operation, and we prune it away. And by pruning, we get like this simplified graph, okay, where this is an operation taking two parameters instead of one for each operation here. Then, still, it is not always necessary to write rewriting rules that take into account also the memory nodes. It might be sufficient to write rewriting rules for like PyTorch modules, like on graphs of PyTorch modules. So what we do now is called projection. So projection is an operation that acts on a bipartite graph. Bipartite graph, remember, is a graph where we have the node set is split in two, and there are no connections between nodes of the same partition, no direct edges, no direct arcs between nodes of the same partition. So by projecting, we select, for example, only the red or only the blue nodes, and we connect them if there is a node of the other partition which connects them. So in this case, you see that like the first node here is not connected to this because there is no blue node. I mean, there is an arc going here, but there is no arc going from the light blue to this one. So these two are not connected. But since there is an arc going from here to the blue and from the blue to here, we connect the first to this. Here we connect, you can, in the same way, you can connect this to this because there is an arc going from here to here and from here to here. So this is like the projection of the computational graph on the memory partition. And this is the projection on the kernel partition, which, as you can see, is a very simple graph with respect to the one that we started from, because we started from this one, which was like, it had 3 kernel nodes and 6 memory nodes. And instead we went down to just 2 kernel nodes. So this elevation is performed by wrapping, but before we perform this elevation, we need that, remember, each operation must be properly scoped. So each operation must be referred to scopes. So analogously to what we did in the lightweight graph editing, we have editors for these, let's say, more advanced kind of graphs. In this case, like ONNX graph. So once you have traced the network, you can wrap it inside an editor, okay? And you can see here that there are unscoped operations. So there are operations that have not been executed under an identifiable scope. What we do to assign a scope to them is using the so-called rescoping rules. So rescoping rules are specific graph rewriting rules that take these graphs. This is like the traced VGG8. As you can see, there are many memory nodes, many operation nodes, and writing a complete rewriting to convert this from fake to true would take like lots of effort, and also we would have to write manually many operations. So what we prefer is instead to rescope manually all the blue nodes, or actually automatically, because I mean, this is exactly what the rescoping rule can do. If in the memory of the PyTorch, if you remember during for those of you who installed QuantLab, at some point you called trace PyTorch modules and trace QuantLib modules. This created an internal library in QuantLib that contains these example templates. So essentially these templates are loaded into memory, and QuantLib looks for these templates in this big graph. And if it finds them, it assigns a new scope to each operation, okay? And after this step of rescoping, all the operations will have a string labeling with the same name as the PyTorch module under which that node was executed during tracing. So which was the PyTorch module under which forward call this node was built during the construction of the dynamically built PyTorch graph. Once you have, again, you see that you have to start up to set the rewriting rule and edit. Once the process is finished, you can shut down the editor. And what you get is a fully scoped ONNX graph. Then the elevation is actually performed when you create this PyTorch graph. This PyTorch graph object in quantlib.graphs is passed a network, a PyTorch network object. So this is not a graph, this is a PyTorch network object, and the traced ONNX graph obtained from that network. And it returns you this graph of, as you see, it returns like the connection of between all the PyTorch modules. So this is like a representation of all the connected PyTorch modules, like with their connectivity. By saying only kernel, we do the projection operation that I showed you a second ago. Here, you see that we have this after elevation, and then we project it to the kernel partition. So what we get, as you see, is like a graph with just blue nodes, right? So now we are ready for the real graph rewriting, which is the one which will lead us to getting a fully true quantized network. So the first thing we want to do when writing this network is creating helper nodes. Unfortunately, I wanted to have the time to explain to you clearly what these helper nodes do. Essentially, what they allow for, I will tell you what they allow for. So these rules, these like add IO handles and add precision tunnel rules, they are rewriting rules that introduce handles that are essentially like identity operations, okay, but allow you to split a graph into units that you can rewrite, but still keep, if you still push a tensor through the network composed by these modules, you will still get the same output, or approximately the same output when not considering errors introduced by the arithmetic folding, arithmetic conversion. So let's see that these are nodes that are like redundant stubs that QuantLib inserts to allow you to rewrite programs that are always functionally consistent to the input model at any moment in time until you get the final true quantized model. After adding these helper nodes, we are actually ready to do the real rewriting. The real rewriting, remember, the goal is to create a network which uses fake quantized, true quantized operations, so PyTorch modules that actually behave the same way the hardware will behave. So we create a software golden model. So we need these kind of structures. If you, for those of you who are curious to learn how this works, here there is like an exercise about the arithmetic folding, and here how you can take in this example, just look through this. Like here, remember, we create manually the graph that we want to replace. So in this case, we were looking for a sequence of unactivation, unconvolution, best normalization, unactivation, surrounded by, as context graph. You see that this is like k-types, this is the context graph. It has helper output precision tunnel, helper input precision tunnel. In between, there is the template core, which is connected in a way that we will see in a second to the context graph. And then we have the replacement, and the replacement will just be a conv2d to which we will feed the ternary weights. This is why we have TW, and a lookup table based activation, which will perform quantization by just comparing integers to integer thresholds. So when building, all the constructor method of this, like this DPO stands for double push out, and double push out because algebraically, when you write these like rewriting rules, you have, remember, you have the left and right, and they share context. So this is called, algebraically, this is called, I mean, these are related to the concept of push out. I mean, it is like a technical algebraic term, but just to tell you that there is two push outs, so this is double push out terms, right? Okay. The name is DPO rule. And this, the constructor is all about building the template. It's all about, if you see, like all these instructions are all like, okay, define K, L minus K, which is the core, the template core, the replacement core. I link, I assign attributes like about the partition, so memory or kernel, and the type of the nodes, so that I can do the type of the morphism checking. And then I link here, I link the replacement to the context, right? So here is all just about describing the template, I mean, the graph rewriting rule, the screenplay, the blueprint of the rule. What instead happens is when you have these apply, okay, so you see that seek is instead the method that looks for application points. So the ghost, you feed it a target network, it will go through your network and will find the morphisms. And it uses these seeker objects to do so. The real meat is in the apply. And in the apply, you pass the target network, you pass the mapping from that identifies the application point. So again, to allow you to undo bad rewriting, instead of operating directly on G, we operate on a copy of the graph. So we have a copy, we find the interface, we find the match core. Then here is where you actually create the new replacement graph. Okay, so we do the core. Okay, where you take the core, the match core, and you produce the substitute core. Then you put the substitute core side by side with the old graph. You link it here. This is like the part that links the old, the substitute core to the interface in the graph, and then you remove the old match core. Okay, and in the core is actually where everything, like the real, let's say, conversion happens, because here you look into the modules. You see that here you look at, okay, this is like the modules that I was looking for. You see that there is like ANA input, ANA activation, like ANA convolution 2D, batch normalization, ANA activation output. What I do is I take their arithmetic parameters and I compute the new folded arithmetic parameters, and I create the new true quantized golden models here and here. And I pass here the true quantized weights and the true quantized thresholds. So the chain of these two operations will behave exactly, should behave exactly as the hardware will execute your network. You can do this, you can see that here, like we started from a network, but at this point here I have replaced like these two modules, because here it found the sequences, so it found two application points. Then we change a rule and we do, here it has found other two application points, so it is replaced this max pool comes to the loot activation. We will go on, okay, as you see, like different rules find different application points. So after applying all the rules, ultimately what we have is a network which, if you see, like contains almost only conv2d and loot and max pooling, which are supported by Qt. Now it is time to remove the helper operations, and this is done by, this is the last step of the graph rewriting, by which you just call this remove precision tunnel, remove input node, remove output node, and you essentially get rid of all these identity-like operations that helped us keeping the unit, the network separated into independently compilable, let's say, translation units. And what we get is this PyTorch network, okay, this PyTorch sequence of PyTorch modules that we mimic the behavior that the network will have on the real hardware accelerator. Here I wrote like a script to verify that the behavior of the fake quantized network is exactly the same. In this case, it is exactly the same. It is bit true to that of the true quantized network, because the input and outputs, I mean the outputs of the two models agree 100%. Okay, this went much like a walkthrough, like than a real like tutorial, or anyway like an exercise, an hands-on session than I expected, but I hope it was sufficiently clear to get a feeling of the steps involved. I will remain here like again for like 15 minutes if you have questions, you want to get clarification, because I realized that I've probably guided you through too much information in a short time span. So if you have, it's very positive you have doubts. It's also very positive you want to go lunch. So anyways, like thank you for like your attention for now. And so before I collect questions, let me tell you something, the last notes. So the softwares can be used in your projects. They are released under the Apache 2.0 license. People that have downloaded that from GitHub should already know this. This is a beta release, so there are still like instabilities. Some of them have already come out. Like I've already tried to help those people that had these issues. But if you will use it, and I really hope that you will use the tool, we will like welcome your feedback. And if you have any, you should address it directly to me, which I will collect, and we will try to take your feedback into account to improve the product. And also I should thank really Georg and Moritz, because they helped a lot with like testing the first like versions of the code and proofreading the notebooks. The issues probably were very likely on me, like those that you witnessed today. And actually, I should also add Manu and Frank for helping with the licensing and publication, because like they are really like kind and assist us like in the last very troubled days of before the workshop. So for those of you who want to go, I really hope to see you at the next edition. Hoping that it will be quite soon, and with a better tool and more time, maybe also to investigate more in depth certain concepts. And okay, if you have any questions, please ask.
Ciao Matteo. I don't have actually a proper question, maybe just a comment, or let's say, for me it will be really great to see a sort of getting started very short about how in practice we can apply the library on some sort of custom problem. So probably this is the main part that probably miss. But probably because I saw lots of material today, so I may got lost a little bit. So I don't know if you have any sort of short getting started with it, or maybe we can discuss in a future, let's say, event.
But getting started, what do you mean exactly? What would you like exactly?
At the end of the day, I need to, let's say, get through quantized models that fits a device. So which kind of APIs I do need to use it, like 1, 2, 3, 4, and that's it.
Okay, so as for this, yeah, probably I went too quickly through the tutorial, because I mean, the purpose of this is that this notebook is exactly intended to present the abstractions. So going from the supposing that you have a fake quantized model, you should use like this ONNX graph abstraction. So I mean, this like was targeting Qt, which is the ternary neural network accelerator that Moritz has developed. Moritz and team have developed, like, and Georg also in the last months. Essentially, this is like a guided like walkthrough to do this kind of conversion for targeting this device. So these are like which abstractions should be used and what you can perform with them. Then something I mean, more than this, probably we'd have to discuss like more specifically the kind of platform that you're targeting, if you want to have like something that fits more your use case.
Yeah, not really. I mean, I don't mean anything specific. Just let's say among the ones you supported already, or that you intend to support in the future.
Okay.
So given that, how do I need to use it? Assuming that I'm probably not an expert of the topic, so I may even not get all the details about graph transformation and so on. So a simple guide for, let's say, less expert people, okay, which may get benefits of the library.
Okay. Yeah, for this, like the notebooks, even like the notebook on the graph editing is meant in a sense to give a feeling of how the thing works and how they are applied in this context. Then, of course, like yeah, we need like probably we need like to have a more specific discussion, like to see, because like these notebooks in my view were intended exactly to provide like this kind of bootstrap to the problem. But yeah, maybe they are like,
let's say, take this as a suggestion. So just for instance, I don't know, if I want to solve the same problem with TensorFlow, they actually need that I need to use an API like get experimental graph with quantization on, and then use few TensorFlow Lite APIs for the transformation of the graph. Then behind of it, they do their own stuff, which I may even not get it. But at the end, you have your own let's say, true quantized models that you can run.
Okay. Okay.
So simple stuff like this maybe would be useful.
Okay.
Thank you anyway.
Oh, thank you.
So I can also say, I mean, we have some, there are examples which run. Certainly for the full precision to fake quantized conversion, there's examples for the packed algorithm, and they also have examples for ONNX. And I mean, theoretically, we have somewhere examples for INQ and STE, but these I think are not really integrated yet, right?
No.
In the newest version. And as far as the graph transforms are concerned, I'm not so sure. But so there is a library of examples at this point.
Hello, so Miguel here. I also agree a bit with the point of the simplifying a bit the workflow for users. So I think you show a lot of material because I'm sure you worked a lot on that, and it seems a bit complex to go through. And as from the point of view of an user, if you want to quantize a network, maybe it would be nice in the future to give these API simple steps that then behind the scenes it's going to be complex, but for the user remains a bit more transparent. That's also my opinion.
No, I agree. The point is that for now we are still, because the problem of, like, from what, as far as we know, the problem of tools like PyTorch and TensorFlow is that they expose to you, let's say, just the straight-through estimator, essentially, for training networks, which is an algorithm which is simple, and they also like make many assumptions on the underlying architecture that will execute the model. So this makes it quite simple to automate this. The point for like QuantLib and QuantLab is that they've been developed like QuantLib more to target exotic devices where you have to do more complicated kind of operations. So I agree that the user might want to ignore these details. At the same time, when you target these kind of platforms, the technological maturity of the compilation, let's say the conversion stack, is not so high that you can hide these details, because they are extremely specific to the platform you are using. I mean, for sure, what we can do is, now that we know how to do this kind of stuff for some networks on some devices, do it. The point is also like to try and let's say encourage people to report about how this stuff breaks and what kind of, let's say, rules they are using. So let's say collect, let's say, a data set of statistics about what people try to do, what they try to achieve. And from there, then understand if we can generalize something. Because when you want to be, let's say, when you want to keep this flexibility of targeting strange architectures or using quantization-aware training algorithms that are not like the simple STE, these things start to get messy. This is the problem. I really see like the desire for a transparent interface, and I believe that the user would like to see this. At the same time, this kind of problem is more than keeping it example-based. It's really hard to try to find an interface that works in very general cases.
No, I see your point, Matteo, and probably nobody here will actually ask for transparent API. I mean, I think most of us is aware that this is a really complex problem, and there is not a unique solution. My point here is to give guidelines, probably, because apart from the research itself on the quantization algorithms, which I find extremely, let's say, interesting and complex as well, I mean, I do see also two other, let's say, possible usage for this tool. One, and probably the first, and with more interest group-wise, is that people would like to map quantized models for application purpose on some given platform. And here probably I'm referring mostly to the PULP platform. So if I think to one of our guy that have an application and would like to map on PULP, probably what what I would suggest to him is to start from an example. So assume that he has his own problem. We can give him an example, a sort of getting started guy, and say, just reproduce the same step. No need to be transparent, just to be, let's say,
linear in the execution, like that it does. Like
exactly. I mean, you have 3 steps, 4 steps, 100 steps. I don't care. I mean, just something that he can reproduce. And this is a sort of, let's say, first getting started, which may be helpful. And then there is the, let's say, the second probably interesting point, which is since we are also does platform, and one of the main point of this tool is to have a sort of platform-aware quantization, which can be customized. No, so there it's a little bit complex because based on what I understood today, you need to modify the backends, then define your own transformation. I mean, this is not easy, and nobody pretends this to be easy. Just probably will be, since this is unique, having a sort of examples also here of the same work done on other platform, then can guide the person to make their own flow for the other platform.
Yes. In fact, like this notebook, for example, this is an example of like targeting the Qt accelerator. We have some examples that I work on with Alessio a couple of months ago for like a conversion of a network using ternary weights and 8-bit activations that we managed to trace with ONNX and deploy on PULP, at least the feature extractor. So, I mean, I see your point. I mean, you say, okay, maybe if we have Jupyter notebooks that are, let's say, they don't focus on the details, but they just explain how to do this for these platforms. Just as quick, like walkthrough that you can just give to people and say, okay, just look here, and from here you can start. If this is what you mean, yes, this is for sure like a kind of, I mean, the examples section is there exactly for this reason. We want to provide, let's say, some collection of Jupyter notebooks that people can use to do their, for example, students can use to start, or people that want to deploy a network and see, okay, this is like a convolutional network, and this uses these rules, and this does this stuff. So is this what you mean?
Basically, yes. I mean, sort of, let's say, different level of examples that someone can take it and adapt for their own purpose. Okay. Let's say this is because actually you explained lots of details today. Those are really interesting, and I mean, I look in the past, and also this material is very hard to find it. So this is as values per se. On the other side, this is a little bit tricky to let's say to understand if you're probably not facing the problem.
Mm-hmm. Okay.
So if you're out of the problem, probably it's not something that you will remember tomorrow in 100%.
Okay. No, I see your point. Actually, your feedback. I mean,
I mean, take it as a suggestion. This is, I mean.
No. It's just that I'm sorry if I like wasted your time. It's more like
no. It's not a waste of time. Don't worry. It's maybe just for giving, let's say, because the interest here is to improve and grow the ecosystem. So let's say having some sort of let's say getting start material that we can, let's say, pass to students, even extracted from the Jupyter that is already there, I mean, will be, for me, will be great.
Okay, perfect. Yeah,
I mean, probably it's already there. Just because for me, I need to check it again, the material, and then probably it's there already.
Because these notebooks, like I thought that I would have been like to go through them like completely, but actually I wasn't. So, but because many details are listed there. But at the same time, yeah, I was not really like, I could not like really walk through, and I also probably wanted to explain like some of the ideas behind. But yeah, I realized that they might, it was like very information packed. Okay, but
thank you anyway. I mean, the work is impressive. Thank you.
Thanks.
And let me one more time. So this will be merged into the public soon. Right now, there is something already there, but for the packed algorithm, so there's a CIFAR 10 examples for packed quantization of a toy VGG, as well as ANA quantization of the same network. And these, they already run the way they are on GitHub, but there are some improvements that I made in the last few days, and now they work even better. And so this will be pushed to the public repo very soon. And this is basically a getting started point, at least for conversion of the full precision network to fake quantized, and then training the fake quantized network. So this is 2 commands that you run, and then you're training.
I have one question. So regarding the this conversions from fake to true and so on, the rules that you have explained are possibly for VGG because it's the network you were using. Do you think it's also valid for networks, these rules? Can we port them to other networks?
I mean, for sure, if you have a network, let's suppose that you have a ResNet, okay? The pattern of like activation, batch norm, activation, convolution, batch norm activation, this sequence of nodes, it is very likely that you will find it even in a ResNet. Mm-hmm. So to some extent, they are reusable. Of course, in some cases, you might want to consider like a broader scope. So instead of considering just these 4 nodes, you want to consider branching patterns of nodes, right? You might want to consider like more complex kind of patterns. So in general, I mean, they are not specific to VGG. This is not, they are specific to in essence, what you're asking is, I mean, the nature of the rule, okay, the template, so the blueprint of the rule, this is not specific to VGG. It is not even super specific to Qt, to an accelerator. If the logic of another accelerator is similar, so for example, if you have another accelerator, instead of running ternary weight networks, it runs 4-bit networks, but still uses a lookup table-based activation, you can still adapt this rule very quickly because it still uses the same logic. Okay.
Mm-hmm. Okay.
So they are quite, I mean, they are quite independent of the platform and of the network you're applying them to. But of course, the moment you say, this is the rule, this is the pattern that you're looking for. So here we say that the full rewriting rule, here you're saying, look for this pattern, look for this specific sequence of nodes. This is the constraint. This gives you the limit of applicability of the rule because it will just look for these specific modules. So if you change fake quantization algorithm, this rule is no longer valid because if instead of using ANA, you use INQ or packed, this rule is useless at this point. Is it clear?
Yes, it is clear.
Other questions? No questions? Okay. So if not, I thank you again very much for your patience. I really hope that you find these like at least interesting. If you start using the tool and you have feedback, again, write me. My mail is you have it for because you have received the invitation to the workshop. So really looking forward to your feedback and hope to see you to the next workshop, maybe with like more time and more structure, let's say, and also like introductory level like guide.
Thank you, Matteo. Thank you very much.
Thank you.
Thank you very much, guys.
Thanks, Matteo. Have a nice day, guys. Thanks.
Thank you. Bye. Bye.
Bye.
Thanks. Bye.